Recording.
Okay. Okay. So I welcome all of you to this workshop on behalf of the cost action called GameNet. This cost action has the purpose of connecting people who do game theory, mathematical game theory in different aspects. And one of the rules of the action is that every year there is a management committee, and usually, actually always, we attach this meeting of the management committee to a workshop. This year, due to the pandemic, the workshop is online and is short. The action has 4 working groups, and the workshop will represent the work of the 4 working groups. So there will be one speaker for each working group. We have chosen young speakers. We have decided to give a voice to the young researchers, so some young researchers in the field. So there will be one for each working group. And this afternoon at 3 Central European Time, there will be a special talk within the seminar, the one-word seminar on mathematical game theory. This is a seminar that meets every other week on Monday at 3 Central European Time. And this is a special talk outside the regular calendar, and it will be given by can you mute everybody? Okay, it will be given by Kostis Daskalakis from MIT. This workshop was organized by Galit Ashkenazi, together with Ines Czech, Tony Kuchera, Panayotis Mertikopoulos, and Miklos Pinter. So I will give the floor to Galit, who will say something about the workshop, and then we'll start with the speakers. Galit, thanks.
So thank you, Marco. Indeed, usually we attach some workshop when we meet to the benefit of usually for the PhD students and the postdocs of the locals of the place where we meet. This time, obviously, we couldn't do that. So we still wanted the younger generation of researchers to benefit of this opportunity. Let me just say we were happy to get the works and the titles. They seem very impressive, and I'm looking forward to hearing your talk. As far as the organization goes, it's going to be a 20-minute talk followed by 5-10 minutes of discussion. People can unmute themselves if they want to ask questions, and well, let's have fun. So I give the floor to the first work group.
And our working group proudly presents Laura Vargas Koch, who is our invited speaker. Laura is just finishing her PhD at Aachen University, and besides writing cool papers, she's also an Olympic bronze medalist judoka, which is pretty cool, I think. So that much about Laura. Are the others also presenting now their speakers, or Laura just goes ahead with her talk? What was the plan?
Laura just goes ahead with her talk. I made her a co-host so she can share the slides and everything. And
all right. Yeah, thanks. Then I start. I was not sure about this. Yeah, thanks for the nice introduction. I want to talk about Nash flows over time with spillback. So when cars actually take space. And this is joint work with Leon Sehring. And yeah, please feel free to always interrupt me when anything is unclear. So I try to explain it as good as possible, but yeah, I'm very happy to take your questions also in between. All right, so what I want to talk about is I want to talk about traffic modeling. And I think, or I hope that I don't need to convince you that traffic modeling is something important. But the question is, how does a good model look like? And to decide this, there are several ideas. And I want to present one model here, which people came up with roughly 10 years ago. And I think this model is well studied and it has lots of advantages. And I will try to convince you of them, but it also has some disadvantages. And one of the biggest disadvantages is that cars don't take any space. And this is what we try to change with our extension. And yeah, I will also try to convince you that this is something cool and important. Yeah, but let's first start with the actual model. And yeah, and the first modeling decision which is taken in this model is to present traffic as a flow. So when we look at these pictures, on the left side, we can see these cars and they are actually there. So this is how we normally would see traffic. And I took this picture standing on a bridge. So we could now count how many cars pass this bridge within 1 second and then could maybe say, okay, it's 3 cars. So then we would have a discrete model. But what we want to do is we want to look at a continuous model. So instead of counting this for every point in time, like for a continuous time, we want to say with which rate pass cars this point in time. So we look at a continuous flow over a continuous time. And this is how we want to come up with a good traffic model. Yeah, and the model which I want to present you is a model which Koch and Scutella invented in 2009. And yeah, they called the equilibrium states in this model Nash flows over time. So we say we are given a graph, nodes and arcs in between. And these arcs, they are equipped with transit times and capacities. And for now, we can assume that the capacity of all these arcs is just 1, and that the transit times are depicted here beside the arcs. And now we say, okay, we have an amount of flow, and this flow travels from the start to the destination node through this network. So let's say here we start at O, we go to D, here's all the flow, and it enters into the network with a rate of 2. And now these flow particles, they split up, they flow over the time through this network and then reach the destination at some point in time. And yeah, so whenever flow from different arcs comes into one arc, then this merges perfectly. And but there could be, of course, some problem. So it could be that the capacity of an edge is exceeded. So we said the flow enters here with a rate of 2. Let's assume it splits up evenly. So 1 unit goes along this path, 1 unit goes along this path. So 2 units of flow go along this arc. But as we said, all the arcs have just unit capacity. So not all the flow is allowed to leave this arc now. So this is why we, or by Koch and Scutella, came up with the idea to put some point queues there. So in the case that the flow rate exceeds the capacity, the exceeding flow goes to this point queue and queues up. And then newly arriving flow just goes to the point queue, and the flow which is in the beginning of the queue can leave the arc. So we have a strict FIFO rule on the arc. So first in, first out. They leave in the time, like, yeah. Those who entered first are also allowed to leave first. So this is the basic idea of the model which they came up with. And in this model, they looked at equilibrium states. So they said, okay, every particle, every single particle is a player, and every single particle wants to arrive as fast as possible. So let's look how can we describe these states. And they found quite a nice characterization. This research was also then pushed further by others, for instance, by Correa, Comenetti, and Larrey, also Neil Olver. And so there's quite a nice characterization of this model. Yeah. And one more advantage, which I think is quite cool, which we have just recently shown, is that there's also a strong connection to a simulation software called MATSIM. So MATSIM is a traffic simulation software which is actually used. So this is used to predict real-world traffic situations. And what they do is they have also a similar situation. They have also a network. They have streets, nodes, and the players travel through this network over the time, and they want to reach their destination as fast as possible. And to compute equilibrium states, so what these people in the simulation software do is they tell the players, okay, 10% of you, they are chosen randomly, and they can recompute a best response. And so they follow a best response dynamic. And then after some time, they say, okay, this is now an approximate equilibrium. So this is some heuristical approach to compute an equilibrium state, which might correspond to the real world traffic situation in a city. And we tried to compare this MATSIM solution to this Koch and Scutella model. So we did this in a simulation-based approach. And we figured out that when we do several random seeds, then the average of this outcome of the MATSIM simulation is like really similar to the Koch-Scutella model. So in this example, it's shown for this breast graph. So we looked at some breast graph, and then we looked at the flow which goes along the top path. This is this flow, along the bottom path, this flow, and along the middle path, this flow. And the points are the flow in the MATSIM simulation, and the lines are the flow in the Koch-Scutella model. So we don't need to go into the details here, but what I want to emphasize is this Koch-Scutella model is really cool because it's very close to this real world simulation. And yeah, then this is what I like a lot. But to achieve this result, we needed to switch off two features of this real world simulation software because yeah, the software is quite realistic and it has a lot of features which are part of real world traffic, and two of them were not part of this Koch-Scutella model so far, and these are spillback and kinematic waves, and these are the features which we included in our model now. Yeah. So let me explain what this is. So what is spillback? So to understand this, we look at a highway, and we have some bottleneck here. And we have also some ring road. So when cars don't take space in this Koch-Scutella model, what would happen when flow arrives with a certain rate, which is higher than this bottleneck, then the flow would build up a queue here at the bottleneck. And then at some point, the flow particles here at the beginning of the ring road, they would see, oh, there's a very long queue at the bottleneck. We should better go along the detour now. And then flow would somehow split up between this ring road and between the shortcut. But I mean, maybe you know this from everyday traffic, so at least I know this because I drive sometimes by car. What happens in reality is that the cars really take space, so they spill back to the preceding roads. So here's actually the bottleneck, but now the cars need to wait, and then it's full already here. So the next cars also need to wait on the road, and the road gets full with all the cars, and they really take space, and then a very long queue occurs. And it's even possible that the queue or the traffic jam is so long that the cars at the end, they have a very long waiting time. And if they would have the choice to just go along the ring road, of course they would do, but they can't, because first of all, they need to wait into this queue until they are here at this intersection, and only then they have the choice. But then they waited already for a very long time, so they still want to go straight on. So this is how spillback really changes also the behavior of flow and equilibrium states, and this is why this is an important feature of the traffic models. And it even goes further, so we can even imagine we have some flow which crosses the road, so it wants to go from here to here, and even this flow is throttled because we have a high congestion here. Yeah, so this is definitely some feature which we want to have in our model, and this is what we will include in a minute. And the other feature which we want to have in our model is kinematic waves. So what are kinematic waves? Let's assume this is a street, and this is a traffic light, and we see the cars from the top. And now the street is full, so it's full of cars, there's no space, and the traffic light is red now. And it turns green. And now what happens? So the first cars can go, and then the next cars will fill up the gaps, and then the next cars will go. And what we can definitely observe in this model is, although there's now some space on the street, so there are some gaps here, no new car can enter into the street. So first, these gaps need to travel backwards on this arc until they are at the beginning, and only then the next cars can enter into this road. So this is what we call kinematic waves. And what you can also see in this example is like always when cars leave the street, then gaps occur. All right, so this is, of course, now a discrete example, but we will do the same thing continuous. All right, so now we can think about how we should model an arc. And what we said is, all right, so we have some flow and we still keep with this point Q. And we say, okay, the flow travels along this arc and then arrives here at the end with a certain rate. And then we say this rate goes to the Q and flow can leave from this arc with the allowed outflow capacity rate. And then corresponding to the flow which leaves, we create some gap flow, which then travels backwards to the start of this edge such that new cars can enter. So this is a basic idea. So now let me, now let me talk about the properties which an arc has. So first of all, an arc has a transit time and an outflow capacity. These are the properties which the arcs had already in the old model. So the transit time is the time the particle needs from the start to the end without waiting. And the outflow capacity is a kind of the size of this hole here, like the rate with which flow is allowed to leave. And now we added some further properties to model all these effects. And one is the inflow capacity. So we just inserted one other hole here. And then the storage capacity. So this is already quite an important feature. One of the, like I would say, the main new feature. And the storage capacity limits the total amount of flow and gaps on the arc and in the queue. So we say, all right, the total amount of flow here in the queue and here on the arc plus the total amount of gaps, this is not allowed to exceed a certain amount. And this is how we can model the spillback and kinematic waves. So because, I mean, you could say, all right, you have still this point Q. This is still a bit like the cars are stapling above each other. But by giving an edge the storage capacity, then we can show that this is the same as if the cars would actually take space on the road. And yeah, the last thing which we added is a backwards transit time. So we said already when flow leaves the arc, then a gap flow occurs. And this gap flow needs to travel backwards along the arc and needs to come to the beginning of the arc. And of course, we need a given time telling us how long this needs. All right. So now let's look at this example here. So we have some arc with some inflow. And now the flow flows along the arc. And now it arrives at the end. But the rate here with which the flow arrives is higher than the outflow rate. So this is why some flow goes to the queue and flow leaves with the allowed rate. And now some gap flow occurs with the same rate. And now this gap flow travels backwards along the arc and the queue builds up further. And now there's some point in time when we say, okay, this arc is full now. So the storage capacity is reached. Not more flow and gaps is allowed on this arc. And yeah, and now we can think about how can new flow still enter into this arc. And of course, something needs to leave. And as we observed already in this kinematic wave example, when some flow leaves here at the end, then gaps of the same size will occur. So this will not make free space. So flow can only enter into this arc when some gaps leave here at the beginning of the arc. Because there the gaps just disappear, so they are not a real flow, they only exist on the arc. And then some new flow can enter into the arc. So the capacity of the flow of the inflow would be throttled to this rate of the arriving gaps. All right. So this is, I think, quite a nice and realistic model. It has a lot of features. If you want to make it a consistent model, so normally you say, all right, a flow needs to satisfy capacity constraints, but then also flow conservation. And for us, there are like a lot of more properties which need to be satisfied to make it a really consistent model and to ensure that flow pushes as fast as possible through this network so that it doesn't wait for no reason, for instance. But I don't want to go into these details, but I want to focus on some other thing. So yeah, I mean, when we have a nice model, of course, we still need some results for this model. And so let's talk about Nash flows in this model. Yeah, and the nice thing is that Nash flows over time with kinematic waves in this model still exist, and they can be constructed by stepwise extension over time. And the idea used to show this is basically comes from this old paper from Comenetti, Correa, and Larrey, and we were able to generalize their idea and their results for our new model. And I will try to shortly explain this. So what we assume is we always assume we have given some Nash flow over time until time theta. And in the beginning, we can just say this is the empty flow. This is the Nash flow over time until time 0. And then we will try to extend this for a certain step. And the first thing is, when we look at this Nash flow over time until time theta, then we can define properties of the network. And what we actually do is we have 4 classes of in which we can insert the edges, and this is the properties of the network we need. So either we say an edge is not interesting at all, so it's inactive, it's not part of a shortest path network, or we say an edge is part of the shortest path network. In this case, I colored this green here. Or we say an edge has a queue. So as we saw on the last slide, it's possible that flow queues up. So in this case, we call an edge a queuing edge. So we look at the network at time theta and say, okay, this edge has a queue, then it gets blue. And the last category is that edges are full at a certain point in time. And based on these categories, we can build up an equation system. And this equation system allows us to compute a certain static flow satisfying all these equations. So there are two different node labels belonging to this, but in the end, this just results in a static flow. And the nice thing is that all particles who enter the network now, like from time theta until time, let's say theta plus epsilon, all these particles, they will follow these strategies in the equilibrium state. So they will split up in this fraction defined by this flow, and this will be the optimal strategies in the equilibrium state. And the only thing which we need to do is we need to compute how long is this flow valid. So, and the flow is valid until these properties here change. So when some edge changes the status, then we need to recompute the static flow. We need to solve this equation system again. And but until this doesn't happen, we can just use the static flow for the next particles and extend the Nash flow. And by doing this, we get the Nash flow until time theta plus alpha or whatever. And then we can do the same thing again over and over until we have a Nash flow for the wished time horizon. Yeah, and to show that this indeed works, we need to show two things are really important. And the first thing which is really important is that this static flow indeed exists. And this is not trivial, so this is quite a complicated equation system. And to find a solution to this is, at least we don't know how to do it in a reasonable amount of time. But we can show by using some variational inequality that there is always such a solution. So yeah, so we can find such a solution, and with this solution we can compute this flow, so we know the strategies for the particles. And now the next question is, so how long is this flow valid? Can we always find a positive time interval such that we can really use this flow for a certain time? And yeah, again, so these properties of the edges, they are just defined by some equations or inequalities, and everything changes continuously. So there's always a positive amount of time for which the flow stays the same, such that we can just use it for a positive amount of time. And so this is quite nice. But then there remains the last thing. So this positive amount of time for which we can extend, they could in principle converge to 0. So it could be that in the beginning we can extend for half a time unit, and then for 1 divided by 4, 1 divided by 8, and so on. And then, of course, we could also not say that we can explore the whole real line. But in this case, we can just take the limit, and again, because everything is continuous, we take this limit point and then we can start again and compute a new syn flow, static flow. They are called syn flows, and yeah, do the same thing again. So this indeed gives us that Nash flows over time with kinematic waves can be constructed by a stepwise extension over time. And yeah, here this should just symbolize this again. So we compute some static flow. So all the first particles go along the straight path. Then some edge status changes, so they will split up. Then some edge status changes, but they will still split up. And then this is a strategy which the particles follow for infinite time, just as a symbolization. All right, so let me conclude. I think that Nash flows over time are a very flexible mathematical model, and I think it's also great that they could be extended in such a way. So the results achieved are originally only for the simpler model, but by giving it additional properties and defining everything appropriate, it was possible to carry all these results over to the far more complex model. So I think this is like a really cool property. I would say the model is quite realistic, so it has it has a lot of real-world features, and equilibria are quite well understood because it's not only that we can construct the equilibria in this way, which I explained, but it's also that the derivatives of the equilibria somehow can always be described in this way, so they can be quite nicely characterized. But there are still two big issues with the model. And the first is that equilibria cannot be computed efficiently. So the static flow cannot be found efficiently. And we also don't know how many rounds of the cycle we need to compute this Nash flow. And the second thing, which is yeah, even a bigger deal, I would say, is multi-commodity situation needs to be understood better. So there are some results for the multi-commodity situation. But yeah, since we talk about traffic, this is what we really should understand, and we don't really understand this at the moment. So this should get better. And yeah, so this is one question which I think is quite interesting. And the other question which I want to present here for as a last thing, which I like a lot, is a question of convergence. So I said that we imagine this flow particles as infinitesimal small flow particles. But we could also, of course, formalize a discrete model. And there's also a lot of work on these discrete models, and equilibria can also be characterized and whatever. And I think it's super interesting to look at this convergence, so to show how this discrete model converges to a continuous model by decreasing the time step size and the packet size. And yeah, I am currently working on this together with Leon, with the guy with which also the spillback and kinematic wave stuff came up with. And yeah, we hope that we will come up with some results soon. Yeah, thank you for listening. Hope that you have some questions.
Yeah, thank you. We have some. We have time for questions, so people just feel free to unmute yourselves and ask.
I would have a question. First of all, thanks a lot for a great talk. My question would be if you think that you can also incorporate lanes in your model, and what effect this would have.
Lanes.
Traffic lanes.
Yeah.
And the reason I'm asking, just to explain the motivation for my question, was because it when you were showing the model for the spillback and the kinematic waves, it occurred to me that you might have a similar effect, you know, when someone changes a traffic lane, in which case you could create a mini spillback or mini kinematic effect. And I was just wondering if these can be somehow modeled, and if you could have any guess of what this could look like.
I mean, of course, you could insert one arc for one lane, right? But in principle, you could always change from one lane to another and this would not be the case.
Yeah, this is
if you have two
why
arcs.
I don't think it would
Yeah.
be exactly like that.
It would not be exactly the same. And then the other thing which we normally would assume is that we just increase the capacity of an arc if we have several lanes. But of course, these effects which you mentioned can also be not depicted by this. Yeah, actually, I think I'm not sure about how we could model this. And I think in this traffic simulation, they have these different categories, right? They have this microscopic models, mesoscopic models, and macroscopic models. And this goes to the grade of detail with which you model a situation. And I think this is something in between. So it has some details, but not too much. And I think, probably this lane situation. I mean, what you could do is you could just model 2 lanes and then insert a lot of nodes and allow for a lot of discrete changes, but also this would not be the same. Yeah, but I think it's a very good question. Yeah, it's interesting to think about how you could maybe still add this.
Yeah, thank you.
Thank you.
I have a question. Can you hear me?
Yeah. Hi.
Hi. I cannot see myself, but anyhow. So in the same, it relates to it. I mean, the convergence also doesn't have to go down to the minimal level, right? I mean, at some point, I mean, you go get. I mean, if you understand the convergence is time-wise. I mean, is that correct? I mean, or when you look at convergence, when you make this fine grid on the final slide, is that?
It's like we need to let the time step and the packet size converge to 0. Is this what you're asking?
Yeah, but why does it have to go down to 0 when the packets? I mean, when the down at a certain level you're down to cars, and then it doesn't make sense to make it more precise. Or am I getting this wrong?
If you just want to have a good model, then I think you are getting this right. And if you want to understand how the discrete model and the continuous model interact or how they are related, then of course we would like that at some point they are the same, right? And
which might be very hard to prove and so on. So I wonder whether it's worth stopping at some point. I mean, that's I mean, it relates to the granularity of the model itself, I think.
Mm-hmm. Yeah. I mean, so what we can prove actually is that the flow embedding is kind of the same in the models if we converge to 0. And why we really want to understand this is because multi-commodity states can maybe better be understood in this discrete model. And then if you can tell how this equilibrium states converge, then you can also maybe understand them in the continuous model. But I see that from a application view, it doesn't make sense to make cars really small. So there's a minimum size, and then that's it.
Okay.
True.
Sure. Just a comment. Thank you.
Thanks.
So I have a theoretical question. Have you considered such optimality principles as earliest arrival flows and the other notions in flows over time, how they react to these generalizations that you introduced?
So in an earliest arrival flow, normally no waiting occurs, right? So you would always assume that all the packets wait at the source. So then you'll not get in the situation that you would have full edges, except if you assume that the storage capacity is less than the inflow times the travel time. So this is actually forbidden in our model, but indeed, I thought about this a bit, and I think it's a very interesting model to look at this optimization question in the situation where you have storage capacities, and maybe not for an earliest arrival flow, but maybe for a quickest flow or maximum flow. Yeah, I think it's a very cool question. Yeah, actually, I asked Martin Scutella about this, and he also thinks that it's a nice question. And from some papers, you can get that you get quite easily a 2 approximation if you reduce the inflow capacity to like your new storage capacity divided by the transit time. But for something better, this would be this is I think a very cool open problem.
I see. Thanks.
Thanks for the question.
Another question.
Yeah.
So you mentioned that the step size that you could go on with the Nash flow could be smaller and smaller and smaller.
Yeah.
And if that happens, you can compute the limit.
Yeah.
Is it possible to compute the limit, or will it be heuristical? Or
yeah, good question. So I think we have the student of the guy with which I did this research, he indeed programmed this, and actually the situation never happened to us, so it was never necessary that we needed to compute this limit. And somehow we are still a bit hoping that the number of phases is finite, but yeah, since we were not able to prove it so far, we need a solution, a theoretical solution for the other situation. Yeah, but indeed, I'm not aware of any example where it happens. So, and for our program, it works without doing these limits. Yeah, so thanks. I think I stop sharing.
Okay. Then we have 2 more minutes until we give the floor to work group 2. So meanwhile, I make Tom co-host. I think I already did, so that they can begin to prepare and share a screen if they wish. Yeah. Perfect. Okay. So maybe we wait 1 minute just not to push the schedule.
Yes, give me the sign.
Yeah. Meanwhile, I can use the floor. I can use the floor to say that we were impressed by the quality of the works that were presented to us by the younger colleagues, and we have initiated as a result of that junior version of the One World Mathematical Game Theory seminar that will begin, I don't remember if next week or the other week. So each work, each talk of a senior representative will be, there will be a 20 minutes talk before that of the younger researcher. So we will send a formal announcement and everything, but if any one of you here, younger generation, wants to be a part of that, you're more than welcome to email us. Okay, I think it's time to give the floor to work group 2.
All right, thank you, Galit, thanks a lot. So working group 2 is colloquially known as Learning in Networks, and indeed today's talk will be about learning theory applied to a network context. I would have to say that usually we are a very pessimistic group, always dealing with worst case results, things like regret, missed opportunities, etc., etc. But today's speaker is going to be much more optimistic because he will be speaking about the effects of cooperation in a network environment when several different agents are learning and communicating between them. And today's speaker will be Tommaso Cesari, who did his studies in mathematics at Milan and also his PhD there, and he just finished. And is now a postdoc in TSE in Toulouse Schools of Economics, and has a joint affiliation between TSE and the Toulouse Artificial Intelligence Institute. So I am very happy and honored to have Tom as a speaker, to introduce Tom as a speaker today. So Tom, the floor is all yours.
Wow, my pleasure. Thank you. Thank you very much for the introduction. And of course, thank you for the invite. Thank you, Lara, also for the great talk before me. Well, let me start my chronometer because I was more gauging towards the 25 minutes. So I don't want to get too much time. And it's true, I will talk about cooperation, but it will be kind of in the same pessimistic worst case lane that you were mentioning before. So at a high level, the things that we will discuss today is indeed when you have a network of agents, all of which are trying to learn a common problem, say solving a common online convex optimization problem. And you can see this happening in a large-scale learning system where usually you have a distributed system, and the communication among agents might be limited due to constraint because of bandwidth or because of a limited range. If you imagine these as sensors, actually the initial motivation for studying these sort of problems came from climate science. So imagine like this picture that I have. So let's make use even of the title picture. It represents a somehow homogeneous region on the Earth, and you're trying to predict some behavioral patterns in the atmospheric dynamics. So say that an agent at some point, like this one, gets triggered because some pollutants or something gets above a certain threshold. And so when this happens, the agent is asked to make a prediction, say, on how the temperature is going to raise in the next 24 hours. Then after all this happens, when the day is over, the agent will get some feedback on this observation. And the idea is that the feedback, of course, can be used by the agent itself to maintain his local model, but it might also be shared with the neighbors that were not activated, but still are in range at the time that this event happened. And the idea of this talk is going to be to give you some overview of some of these variants of this problem and some of the results that are out there, mostly by me and the person I work with. So this is a joint work with Nicola Cesabianchi, who was my former PhD supervisor, and Claire Monteleoni and Riccardo Della Vecchia also. So let's kick things off with a quote that I blatantly stole from Nicola's old paper, which is, only a fool learns from his own mistakes. The wise man learns from the mistakes of others. This is kind of the leitmotif of this whole setting, how we can improve the overall learning of the system by exploiting learning of others. So, okay, let's give a brief. I will try to keep it as high level as possible, and just to give you the high level ideas that I think that's in this case are more important than just give you all the details. So consider a network of agents, which in math terms is just an undirected simple graph over a set of, say, n integers. And at each time step, the environment picks a loss function, say some convex differentiable function defined on a subset over D, and a set of active agents. So the important thing here is that the active agents are not decided by us, by the learning system. It's decided by the environment, like in the example that I gave you earlier. And I will clarify later how these activations work. Now, when an agent is activated, as in the example, it will be asked to make a prediction, then it will suffer the corresponding loss, and then they will receive some sort of a feedback, which we will also talk about again later. So the cooperation part is that after the round is almost over, agents are allowed to share information with their neighbors. And the type of information could be just the feedback that they received, or it could be something a little bit more, maybe some information about their local model that can be shared with the neighbors in the network. And the idea, again, is unexpectedly for people from this pessimistic group, is to minimize some notional regret, which is defined simply as the difference between the cumulative loss of all the active agents and the loss of the best action in hindsight. So let me just clarify the things I was a bit vague before about. And as you will see, I will give you a whole bunch of knobs. And depending on how you turn these knobs, you will have different instances of these cooperation problems. And so by the end, you will have your combinatorial amount of problems that you can solve. Some of them will be solved already, but some others are still very much open. So how activations are, how agents are activated could be adversarially. So maybe you want to be competitive between activation chosen by an adversarial environment for each individual sequence, or stochastic. You might assume that there is some underlying stationary distribution, and agents are just IAD draws. I mean, the activation of just IAD draws from the distribution. Could be just one agent that is active at each time step, could be more. And you can have all sorts of feedback. You can have full feedback where you see the whole loss at the end of each time step. You can have banded feedback where you only see the loss of the action that you played, semi-banded, you name it. Now, another important thing is the propagation of information. Like when you have no propagation, you're just saying that if you're a node, you make your prediction, you get your feedback. You can share your feedback with your neighbors, and this feedback never leaves your neighborhood. When you have propagation, on the other hand, you allow people over rounds to propagate this information throughout the network, and so possibly reach nodes that are further away, agents that are further away. So just to kick things off, we will start with just a single agent activation, full feedback, and no propagation. And then we will see some other possible configuration. Actually, for the most of the talk, I will focus on single agent activations, and at the very end, I will tell you what changes with multiple. So just a quick sanity check to establish a benchmark on what we could expect from cooperation, which is what happens if you don't cooperate at all. So let's say that each of the agents in your network is running their favorite optimal single agent online convex optimization algorithm for a certain number of rounds. And let's say that T is deterministic, just to make things simpler. So each one of them will suffer a regret, which is the order of square root of the number of times that they played. Since this is a partition of all the time steps, like a simple Jensen inequality tells you that if there's no cooperation, you at least would expect to get a square root of T bounds that's scaled with the number of agents. So the whole idea is we want to beat this rate because the number of agents could be very large. We don't like it. We would like something which is more reflective on the connectivity of the graph. So some sort of metric that tells you how the graph is connected. And okay, before going forward, let's also discuss briefly what type of algorithms we would like to use. And the basic idea is we want them to be simple. Like whenever we have a distributed setting, we would like things to be as simple as possible in case, for maintenance reason, in case something goes wrong and we have to replace like physical components or whatever. And this is sort of the simplest interface that we could think of at a time, which is just a one single agent algorithm. And all the nodes are playing the same one. Let's imagine, for example, online mirror descent. Everybody's playing online mirror descent. Not only that, they're using the same initialization and the same learning rates, so you don't have to do any node-specific shenanigans. And everybody makes predictions / updates whenever they get the opportunity to do so. So they get some feedback from somebody, they use it. In this sense, the interface is oblivious in the sense that it doesn't matter if the feedback comes from yourself, if it comes from a node that's your neighbor, your second neighbor, you just use everything without caring about the topological structure of the network. So let's see if this very simple interface can be used to get some results. And the first result is a hard no. If activation are adversarials, so even if just one node is active, let me recap. We're just assuming that one node is activated at each time step. There's no propagation. People just share their feedback. And if activation are chosen adversarially, you can find a graph for which no matter the algorithm you use as a base algorithm for your own oblivious network interface, you will always get a linear regret. So no learning whatsoever can occur. And to give you the reason why, I will show you this picture, which is worth a whole proof. I will also lie a little bit, but with cheating a little bit, you will get the right idea though. So imagine that the graph, your network, is a star. So there is a center, the center node that is very well connected, and everybody else is just connected with the center. So strategy for me, if I'm the environment and I want to really be screwing with the learning system, is first, okay, let's make it even simpler. Let's not even do some fancy online conflict optimization. Let's do some learning with expert advice. with 2 experts and with linear losses. So you only have 2 arms, and each arm gets either 0 or 1 loss. So it's as easy as it gets. What I can do as an environment is the following. So I draw one of the 2 arms at random, and this would be the good arm, so the arm that's going to be optimal in hindsight. And at each time step, I draw 1 node uniformly random among all nodes. And if the node is a peripheral node, then I will show you the correct losses. So I will show that the loss of the good arm is 0 and the other one is 1. If the activated node is the center, I will just flip them. If I do it this way, what happens is that the center will see everything, no problem. However, the center will also increase the spread of bad information, because each peripheral node will be activated roughly the same amount of time that the center is activated. So they will see the same amount of good and bad feedback for both arms, and they will henceforth be unable to distinguish the two. So with a simple argument, you can show that any algorithm would have a linear regret. Single agent algorithm for the peripheral node will have a linear regret, and so the regret of the whole network, which is just sum, is linear also. So this is just to say that adversarial activation are their own beast. Of course, there are workarounds, like as I told you before. For example, if you ignore all communication, you can have sublinear regret. You can do something fancier, like you can say, instead of using the actual topology, I partition the graph in cliques, and I only listen to people, I only share feedback with people in my own clique. Like if you do this, you can kind of see that everybody in the clique has the same state, in the sense that they make exactly the same feedback. And so you can kind of maybe see that you would scale in this sense with the clique covering number, which is the smallest number of cliques needed to cover a graph. You can do something even fancier if you allow agents to share the local model also. Like in this case, okay, I will tell you first the node, and then in the next picture I will show why this works. Where I will give you a pictorial proof by picture of why this works. And in this case, you can scale with the so-called domination number that you can think of as the smallest number of stars that you need to cover a graph. So let me just give you a picture of the 3 cases before, just to give you some high-level intuition of how things work. This is the quote-unquote bad graph in this setting. It's a star. We said a workaround is assuming that people actually don't communicate with each other. This means that actually the graph that they're using in their learning is no longer a graph, but they're purposely ignoring a whole bunch of arcs. And what they're using is just a completely disconnected graph. And you get this bound. What happens with the clique covering? Well, kind of the same thing. You purposely ignore some of the arcs between agents, and you only communicate among agents in the same clique. And here you can see that in the same clique, you basically act as your own unique agent. So in the end, you will scale with the number of quote-unquote independent units, which is exactly the number of cliques, which, I mean, in the worst case that you can see can be almost as big as n. So this is not awesome. Something which is much better, but you're using more knowledge, you're sharing more knowledge on one nodes, is if you cover with stars instead. And of course, the smallest number of stars that you need to cover a star is just 1, just the star itself. And in this case, you can kind of see that if everybody share their local model with everybody else, in particular, the central node will have access to all the local models of everybody else. And this is just to give you a high-level idea. It doesn't matter if you don't get fully details, but it's indirectly as if all the nodes would have access to all the information of everybody else. It's not directly, it's indirectly, but it's kind of what happens. So pictorially, it's like instead of having just a star, you would have a full clique in terms of the amount of information you have. And so you can scale it with this number, which is much lower. So in general, this is just the graph theoretical stuff. The independence number is always smaller than the clique cover number, which is always smaller than the number of nodes. And as you can see, there is another little guy here, which is the independence number, which I will introduce next. Where I also move away from adversarial activation and talk to you a little bit about stochastic activation. So the independence number of a graph is simply the smallest the largest cardinality of an independent set. So the largest cardinality of a set of nodes, no two of which are adjacent. So in this simple example where we have only 5 nodes, you can see that nodes 1 and 2 are independent in the sense that they're not adjacent. And if you think about it for 5 more minutes, you can see that you cannot find 3 agents that are all independent. So 2 would be the independence number of this graph. Now, with this in mind, you maybe kind of see this lower bound that you cannot do any better that scaling with the independence number of the graph. And the reason is the following. Think about the graph, any graph, doesn't matter. If activations are stochastic, you can just take a distribution Q that is supported on an independent set. If you do so, since we are only sharing the feedback, and we are only sharing it locally, so it never leaves the neighborhood, say that at some point node 1 is activated. You get some feedback, it shares it with the neighbors. Who cares? We are supported only on 1, 2 for now. So 2 never get to see any input coming from 1. Similarly the other way around. So basically this way, we reduce our problem to the problem of alpha, where alpha is independence number, alpha independent learning agents that are trying to do their best. And we can apply the same reasoning that we applied before to get the square root of nt, where this time the number of independent agents is just alpha. So this is not random. It's actually the right worst case rate, because you can show, we did it with online mirror descent last year, that if everybody runs online mirror descent with this network interface, you can indeed reach this upper bound of square root of alpha t. And I will just give you 2 nuggets for the proof. I will not give you the proof. This does not imply the proof at all. It's just 2 important aspects of the proof. So first of all is the probability of making an update, which is just the probability that a neighbor is active. Since we are in a stochastic environment, now it's independent of time. So this is the big difference, and that was the reason when you went ahead and do the computation, was the reason why with the adversarial environment, you could get screwed, and in this one, you could not. And the other idea, this seems like a kind of random thing to write, because I'm not even going to tell you why this, where this comes from, but it's not so random. So this is just a simple, again, graph theoretic inequality that tells you that if you have a distribution little q on the set of nodes of a graph, it's always true that the sum of the probability of the node divided by the probability of the neighborhood of the node is at most alpha. So again, this seems kind of random, but the reason why I'm telling you is that if you see these papers on cooperation and you see bounds that have alpha in them, you can be fairly sure that sampling of this appeared in one place or another. And this is quite nice because it's just something that depends on the graph. It doesn't have anything to do with the learning per se. Okay, so now let's move on to non-full feedback settings. And let's discuss propagation also at the same time. So in this picture, let's say that a node VT is activated at a certain point. You get some feedback, and at the end of the round, they share the feedback with possibly some local information about their state with the neighbors. If we allow propagation, what happens is that the following round, these nodes that now they got some information, they can push the information further, and then again, and in the case of this simple graph, in 3 rounds, information would have reached the whole the whole graph, the whole network. And the reason why, I'm getting a long time. The reason why I'm telling you, so I will skip some details later. The reason why I'm telling you this is that think about from the perspective of this node, which is not active. Like imagine that you're this node and forget that you're part of the system. Just think about it from your own personal place. From your perspective, at some point, a loss has been generated. You don't see it. You don't see it the round after, but you do see it 2 rounds after that. So from the perspective of each nodes, it's like the node is playing a single agent online learning problem with delayed delays. And this is kind of the idea of the reduction. This is still ongoing work, but they will be published soon. So I will do my best to cheat and pretend that this is super, this is as easy as it is. It's not exactly, but the high level idea kind of is. The high level idea is if you run an algorithm with an oblivious network interface, from the perspective of the nodes, this is what's happening. So before giving you the result of the reduction, let me just give you a definition, which is the generalization of an independence number. This is that something is the diff independence number of a graph if it's the biggest cardinality of a set of nodes, not to which has distance d or less. Instead of 1, it's d or less. It's also called the packing number, a distance d, if you know this from somewhere else. And the idea is the following. If you already have an algorithm, single agent algorithm, and you know that this algorithm works well with delays, which is the case for most popular algorithms, or linear descent, for the perturbator, whatever. So you have your bound, which is like square root of t. I'm ignoring constants everywhere, by the way. I'm being very sloppy with the, I'm just talking about rates here. Don't be mad for that. So if you have your algorithm, which case with the t, with the time horizon, plus the sum of the delays, which is what happens with these optimal algorithms. Then if you run that algorithm with an oblivious network interface, if you kind of believe, if you have it within you to believe that this is just what happens from their perspective, you can kind of see that this is going to work well with the system. And quantitatively, this rate, square root of t plus the sum of delays, translate into square root of t multiplied by this constant. This constant is the diff independence number plus d, which is in this setting is the maximum delay that you're allowing, the maximum propagation that you're allowing. And as you can see, you have this sort of trade-off, because the more, the further you allow information to go, so the bigger the d, the smaller the alpha d, the less, it's harder to get to points that are far apart. So it's hard to find many points that are very distant. So when d increases, alpha increases and d decreases. And of course, there is an optimal one, which again, it's kind of nice because it only depends on the graph. This is just something that you can compute. Well, computing actually is not as easy, but in principle, it's well defined from the graph. And this applies to not only full information, as we discussed before, but also bandit, semi-bandit. Pretty much everything translates in this reduction. You can do it with oblivious network interface, which is quite nice. So very quickly, let me just tell you what happens with the multiple activations. And in terms of results, pretty much everything stayed the same. So with multiple activations, usually you model it by saying that each of the agent has their own fixed probability of being activated. And at each round, you just make an IID draw and see who's active and who's not. And same result that you get, pretty much, you get it with the multiple activations. The proofs are a different story. Like proving stuff is not as easy, even though the results stay the same, because now you have all sort of superposition stuff. I mean, I will not get into the details, but just know that there is some things to be addressed. And let me just conclude with some open directions, because as I told at the beginning, there's all sort of knobs that you could explore, and we only saw a subset of them. For example, in the adversarial setting, we barely scratched the surface. So we saw that with this oblivious network interface, we couldn't really do much. And we saw some very simple, because the things that I told before, if you think about it, they're not super smart. It's kind of the first thing that you could think of. And what is sort of the minimum amount of additional knowledge that you need in order to make the adversarial setting work? This is still very much open and not understood. And when you understand that, of course, the next step is going on to adapted environments, because I didn't tell you earlier, but the lower bound that I built earlier, the linear lower bound, you didn't even need to be adaptive. You could just screw everybody with an oblivious adversary, which is quite tricky. Also, one thing that I kind of hid under the carpet is that in the full information setting, you really just need to share the feedback. when you add impartial information, though, you need to share also some local information about your model. This is really needed to make the theory, the things that I hid, the technical things that I hid work. And while the way that we did it work, it's not clear what's the minimum amount of information of additional information that you have to share among nodes to make these reductions work. Finally, we had this oblivious network interface, which for us was the kind of the simplest type of model, but of course it's just a type of model, which made sense to us. And in principle, you could think of many other that would also make sense. So this is pretty much everything I wanted to say. I was 5 minutes late as I was afraid I was big, but I got there. So thank you very much for your attention.
Thank you very much as well. And before perhaps going to any questions, if there might be, Galit, just to check, how much time do you think we would have?
Like 3 minutes, maybe.
You have about 5 minutes before we're taking 15 minutes break. So 5 minutes, but a little bit flexible.
All right. So let's say if you have any questions on Tom's talk, now is the time to speak. Just unmute yourselves and ask away.
Hi. Hello. Can you hear me?
Yeah.
Yes.
It's a bit low, but.
Well, I have one question. If I understood well, you assume the common loss for all agents. Is it so?
Can you please repeat? I assume.
You assume common loss for all the agents.
Yes, exactly. Everybody's solving the same problem.
It means that all your local models operate on the same variables. They predict the same variable. Is it so?
Yes.
So could you consider, for example, complementary, because each agent can be different and can observe different environment, partial environment, and they can share different opinions about the same variables. Enriched by external observation. Have you considered that or not yet?
Yes, this is an awesome question. Actually, it's kind of the natural second step, because at the very beginning, we were really just thinking about everybody solving a common problem, and as you put it, kind of measuring the way in a similar way. But what you said is kind of the end goal, where you would have probably not so different losses, but different losses nonetheless. That depends on the node. And the idea is, can we, in this case, just keep similar theoretical guarantees? And we do have some preliminary results. It's kind of very partial results, I have to say, like under additional assumptions. But there is something that works well because all losses are the same. So what I'm trying to say is, yes, the question is very much worth exploring. Actually, I forgot to write it, so thank you very much for asking this question. Yes, you can. Actually, we already have some preliminary results, but the extension is not a simple extension. It's kind of their own different problems. So yeah, this is what I can say about that without spoiling too much. No, actually, this is everything I have to say about this. But yeah, thanks for the question. It's a great question.
Are there any other questions?
I know I talk a lot, guys. I'm sorry. It's a problem.
No, I'm actually asking because I also have a question, but I don't want to take anyone else's time.
I have a short question. When you say adaptive environments, what do you have in mind?
So what I mean is right now, the environment in the adversarial setting that I described, before the game begins, they chose a sequence of losses and a sequence of activations. You can imagine as chosen before the beginning of the game, and it's independent of the player's choice. In an adaptive setting, the learner chooses the first loss and activation. Then the learner reacts, and then the choice of the second loss and the second activation could be a function of the observed actions of the learner. That's what, and it's of course significantly harder. Like usually you have worse regret bounds, but you can do things sometimes. So it's definitely something interesting. You're welcome.
All right. Well, we are already at the half-hour mark, so I will keep my question offline. And thank you again, both to you and Laura for this great beginning. I don't know if Galit has anything to add, but I would also like to thank her for putting everything together. And
thank you very much. Also.
Thank you guys for your talks. I wish I could serve you actual coffee, but I cannot. So let's just take 15 minutes break for refreshment. And yeah, I can see that. And we'll meet you all in 15 here. I'll pause the recording.
Markov decision processes, or POMDBs. And our speaker is Raimundo Saona. He's currently a PhD student at ISD Austria with Krishnendu Chatterjee. And okay, I simply pass the floor to him because I think we are more eager to hear what he has to say than what I have to say. So, okay, so please, Raimundo, start.
Thank you very much for the introduction. Do you hear me well? Just to check. Yes, great. So I want to present this topic as easy strategies for complex games. And easy strategies is more like, well, a computer can implement it. So you might think it's not so easy, but it is because the game is really complex, and we will see why. So implementable by a computer, it is just a strategy that uses finite memory, and the complex game is this POMDPs with a particular objective, which is the long-run objective. And we will also comment, hopefully, some other objectives. I work with Krish and with Bruno in Paris. So POMDPs, yes, this is a stochastic game. It is in a graph. There is only one player. And from the most simple model, like Markov chains, there you introduce one player, there's Markov decision processes. If you introduce hidden states, there's hidden Markov chains. And now if you combine both of them, you get this POMDPs. So, and an idea or an example of how it looks is like this. The player is given the whole structure of the POMDP. So he knows how many states there are, how many actions there are, and there is a reward function that once you pick an action, given the state, you get a reward. But all the dynamic is imperfectly observed by these signals. So once you are in a state, the action determines the reward and the signal and the transition. So it determines a lot. A concrete example will be this. You have two states, up and down, actions up and down. The transitions are the same for both actions. And the only thing that differs is the payoff. So if you are in a state down and you play action down, you get 1, if not 0. If you are in a state up and you play action up, you get 1. So imagining that the player knows that the initial state is up, she can play optimally, just play up, up, up. And when she knows that goes to the other state that transited, we'll play down, down, down. Now this is imperfectly observed. So the player doesn't know exactly where the state is. So how will she know if she has to play action up or action down? There are these signals. So each of these transitions have signals. And in this case, the signals are wait if you stayed in the same state, or change if you moved to one state from one state to the other. So in particular, if the initial belief is not just one state, you know where you started, but you know that you start here with probability 3/4 and here with probability 1/4. Now you have some uncertainty about where you are. You don't know. And well, if you go, okay, most of the time I'm up, so I will play in the beginning up. I get a signal with a signal weight. All I know is that wherever I was, I didn't move of state. Then if you keep playing action up, you might get a signal change. And say, okay, now this probability is changed. Now my belief over the state in which I'm really in is 1/4 and 3/4. And you can keep playing. So as you see, the only thing that you get are signals. In this example, the uncertainty you have over the state where you are never decreases. And this is the stages, and you get some rewards, but you don't see the rewards. Still, you want to do it the best you can. So the specific objective that you have doing it the best you can is aggregating the rewards that you get at the stage M as, well, the average, and we have the objective of very patient players that care about the limit of the average. The limit average might be a random variable, therefore we have to put the expectation. And well, the value of the game is the supremum over all possible strategies. This value of the game is not arbitrary. It has been studied by far the most among other objectives. And it coincides with the limit of a finite horizon. So when you only care up to n stages, or the discounted, right? When the discounted goes to 0. So this is different than, this value has many properties. And what we want to study is how complex the strategies that achieve this value have to be. So recalling in different contexts, MDPs, where you know the state, can be solved, or you can get the value. You have epsilon optimal strategies, which are stationary, meaning that you have a map from state to actions, and that is good. In the case of POMDPs, it's not that easy to get epsilon optimal strategies. Blind MDPs, meaning that there is only one signal, which doesn't really help you a lot, because if you play an action, you get that signal. You play an action, you get that signal. You don't get the information. You have something which is belief stationary epsilon optimal strategies, meaning given your belief, you map to an action. And that is good to obtain the value, to approximate the value. There are other POMDPs which have ergodic structures where there is randomness and everything is IAD, where also belief stationary is good enough. Now, in the general case, POMDP, we show that finite memory is good enough to approximate the value. And finite memory is maybe different than belief stationary. Belief stationary is a map from belief to action. There are infinitely many beliefs. So a general map from belief to action might not be finite memory. And it is a very intriguing open question that we have. How complex are these belief stationary maps? And we don't have examples that show that there is epsilon optimal belief stationary maps for blind or for ergodic or for POMDPs, and that they cannot be encoded in finite memory. In the same way, our finite memory is not belief stationary. So we use finite memory in other sense, some other way. Some words about the POMDP and why we like POMDPs. I like POMDPs because it takes care of this seducing but irreversible actions. So there is this chest of gold that we might want to get, but after making this decision, we just go to hell and we get 0 afterwards. So if we care about the long run objective, we might better choose one coin at a time, because in the end we will get something. Otherwise, here we get nothing in the end. And if one approaches this like, I want a good strategy for the limit game, but I don't know how to compete it, so let's consider a finite game and let's go with a good strategy for this finite game. Well, most of the cases, the good strategies for the finite game will choose the chess, but that is just a bad idea in the long run. So we have to approach this from the beginning in the limit case. Now, I said that this problem is really hard, it's complex, and it's complex not because it is NP complete or exponential time or p-space complete. It is undecidable. It is undecidable to approximate it. So it's a very pessimistic or difficult place to be. If the value of the POMDP is this V infinity, this is the initial belief, it is impossible to come up with an algorithm that gives you back this value V that is epsilon close to the value of the game. This is just like halting in Turing machines. There is no Turing machine that, given an algorithm and given an input, tells you if it stops or not. So what do? Where we don't give epsilon approximations, but we give lower bounds of these values so that the supremum of these things achieve the value of the POMDP. And in turn, we also prove that there will never be an algorithm that gives upper bounds for the value of POMDPs. Why? Because, well, if you combine the two algorithms, if these upper bounds existed, if you combine two algorithms, you will give an epsilon approximation. Also, there is a consequence here. So we know that finite memory is good enough, but just how big of a memory? What practical question will be? Well, you cannot know how big of a memory, because if not, you will have an epsilon approximation, which is impossible. Another consequence is the continuity of the value function. So in this setting of POMDPs, you have the states, actions. If you introduce a new state, of course, it's vastly different and the value might be vastly different. A new action is also complicated. If you perturb the rewards that you get, it's a state, action gives you a reward. If you perturb the rewards, of course, with this objective, the value that you get will be continuous upon this perturbation. What happens if you perturb the transitions? So you're in a state, you take an action, you know which are the possible transitions. If you perturb the probabilities a little bit, does the value of the POMDP change just a little bit? Yes and no. So in principle, for example, introducing a new transition, for no matter how small it is just as introducing a new action. So this is a no-go. And for this to formalize it, you have to introduce a metric over the transitions, where it is not just a small probability, but it is more ratios of probabilities that change. Now, understood a perturbation of transitions in this way, where you don't change just the probabilities a little bit in absolute value, but in relative value, we prove almost continuity, lower semi-continuity. I really think that the real result is continuity, but we don't know how to prove it. And I will comment more later what it means to be lower semi-continuous. Okay, So to have an intuition of how these things work, I have two ideas that I want to give to you. Is the most recent history enough to approximate the value? We know that we need finite memory. Could we just use the last history? That's one question. The other question is, we find this objective and we have the lim inf here. What happens if you just change it by the lim sub? Like, how much could it change? It doesn't seem that it changed too much. It's already the limit of the average. The answer here will be no in general, but it is enough in blind MDP, meaning when there is only one signal or no signal at all. And here the answer will be finite memory is not enough to approximate the value. So for the first question, is finite recall or just the last actions enough to approximate the value? The answer is no. And I want to phrase it in a very simple way. If you start with a state and you get a signal meaning you do any action, you get a signal, meaning you will go to a subgame here. In this subgame, there will be only one optimal strategy. And if you deviate from this optimal strategy, you get 0. If you don't, you get 1. If you go to this other subgame and you play the same optimal strategy than in the left, in the first subgame, you get 0. And there is also only one optimal strategy, and if you deviate, you will get 0. So it is very important to know in which of these two subgames you get. Moreover, this thing that like optimal strategies are very similar, but slightly different. And this is slight difference in the long run will just, the value will be vastly different. So the exact example is like this. In this subgame, you have two states. You start in the up state, and if you play action A or up, you stay there and you get a value of 1. So this is great because this is all you want to do. You will always play action A. If you ever play action B, you go to a bad state and you stay there forever. Okay, now the second subgame. There are 3 states, up, middle, down. You first want to play action A. You might stay or might change and get a signal that you changed to the middle stage. And then you want to play action B to return to the upper state and then go back and playing action A many times. So again, if you deviate once, you choose the wrong action, you go to 0 or you go to 0 and you lose forever. So the thing is, here you want to play action A forever. Here you play action A many times, then once B to come back to A. One, and then suddenly you get signal S2. So signal S2 could mean, hey, you have to change action, or could mean, no, you don't have to do anything. How do you know? Well, you know, depending on the first signal you got. If you got this signal, you don't change. If you got this signal, you have to change. So this shows that you cannot forget about the initial signals in general. Good. Just checking the time. Okay. This example is also short. What happens when we change, or more shorter than the other? So what happens if you change the lim by the lim sup? Very simple game. You either choose to change the state or you choose to stay. The thing is that the reward is only one in one of the two states that there are. Okay? Now, imagine that the initial belief is a half and a half. So you are in one of the two states with equal probability. If you play stay forever, you will get one half of the times and 0 1/2 of the times. So your mean will also be either 0 or 1. But to take advantage of the lim sup, you could do the following strategy. You could wait for a long time so that the mean is big if you were in the state, then change once and wait for even longer period of time so that your mean also goes up. So if you look at the mean, it will, no matter the state where you started, it will look like goes to 1 and then goes to 0, goes to 1 and goes to 0, and goes to 1 and goes to 0. So the lim sup will be 1 in both cases at the end. And the thing is that it will go to 1, go to 0, that the times that you have to do one action, it just increases over time. So this cannot be encoded in finite memory because you run out of memory. So there is no hope that for lim sup you have finite memory strategies, nor just belief stationary strategies. The belief here is always the same. Good. Open questions. I have already kind of said some. I really think that the value of the POMDPs are continuous, which we just proved there was some continuity. Another thing that we want to, or we wonder, is another kind of strategies. We know that this map from beliefs to action might be epsilon optimal or might not. And we wonder if there is any finite memory version of belief to action strategies that can also be epsilon optimal in a sense. They can also approximate the value from below. Meaning that, yeah, so if you have your simplex and you have a partition and decide an action for each of the set of the partitions, can you somehow first follow the probability, follow your belief, and second have an epsilon optimal strategy? Another things that might be, so POMDPs is difficult, so it's undecidable because we cannot give an epsilon optimal. Is there simpler POMDPs that can be decided? And the last one, I will just briefly, is to change expectation by probability. Probability over what? You have this random variable, and we want it to be at least gamma to optimize for this. For this, we have some ideas, and this one we are working on currently. That's it. That's the talk. Happy to take your questions.
Okay, so are there any questions? Okay.
I have one question, maybe if I can ask a question.
Yes.
Yes, I'm curious about this lower semi-continuity that I was trying to think about during your talk. What is the reason that lower semi-continuity is easier to deal with here than upper semi-continuity for the continuity of the value function?
Yes. So
it's probably a kind of technique that is present there, which you cannot use for upper semi-continuity, or what is it exactly?
exactly. So once you fix a finite memory strategy, the dynamic is a Markov chain, right? Because so in the memory state and in the state itself of the game, everything is Markovian. You fix the strategy. Now, if in a Markov chain you change the transitions a little bit, then the value of this Markov chain will also change a little bit with an inequality, not continuous from both sides. And the thing is that when you included the finite memory strategy, so you have a POMDP with a fixed transition, you have a finite memory for this, you have the inequality having fixed the finite memory strategy. It doesn't have to bound by above the value of the new POMDP with the new transition. So it comes as a consequence of continuity for Markov chains, that it is only an inequality and not epsilon approximation.
Okay, thanks.
Okay, any other question? Okay, so let me use this opportunity. So you mentioned this result about finite recall strategies, which are not strong enough to approximate the value, right?
Yes.
And my question would be, so according to your example, it seems that the decisive point is that, you know, at the beginning you have this state, you need to remember to make an appropriate decision.
Yes.
So natural naive idea would be, so what if your MDP has the property that you somehow have to visit every state regularly, like the structure guarantees that you will arrive to every state in at most, I don't know, k steps or something like that. So if your MDP has this structural property, so do you think that the result still carries over, or you could somehow formulate the result that saying that the finite recall strategies are sufficient in this natural subclass of POM-MDPs?
Yes. So for simpler POMDPs where you know you have control, no matter what you do, you can reset the game, you can restart. Then the answer is yes, finite recall is enough. And we're wondering about the good class, because being able to reset the game is kind of strong. Once you start working, you say, yeah, it's obvious if you can restart the game, then everything has the same value. Just how more complex can these POMDPs be?
Okay. Okay. So is there anything else? If not, then I think the time is almost up. So let's thank our speaker. Let's clap, at least virtually. Okay. Okay, so I pass the token back to whom actually?
To our group. Yeah. So thank you
okay.
for this talk. And now it's work group 4. So that's me. That's me presenting. So I'm happy and proud to present the speaker of work group 4. We have Dima Scheiderman. He's studying for his PhD in the School of Mathematical Sciences of Tel Aviv University, where he did his previous degrees under the supervision of Ehud Lehrer. He has a very nice paper in MOR about a new characterization of exchangeable processes in terms of posteriors, but I think today is going to talk about something different, and I'm curious to hear. So Dima, the floor is yours. You're a co-host. Please go ahead.
Thank you, Gali. Thank you very much for this opportunity. So today we will talk about repeated games with incomplete information on one side, with some new class of dynamics, predictable ergodic ones. This is a joint work with my advisor, Ehud. And to start, let us review briefly the model of repeated games with the incomplete information on one side, which was first introduced by Aumann and Maschler in the 1960s. So we have 4 parameters to the model. We have a finite set of states denoted by K. We have a probability distribution over those states, P. We have I and J, finite sets of actions for players 1 and 2 respectively. And we have a scalar function which assigns to every state and pair of actions a scalar. So this will be a zero-sum game. And let me introduce the n-stage repeated game, gamma n of p. So this game will be a zero-sum game with incomplete information, and its play will proceed by steps. So at the first step of the game, nature will choose some state k according to the distribution p. Player 1 will be informed of the chosen state. Player 2, however, will only know the distribution p. At every stage n, small n, both players will choose simultaneously actions in and jn in their action sets, and those pairs of action will be publicly announced. And in the end of the game, the total payoff to player 1 will be the average per stage payoff along the game. Okay, so one question which one can ask is how does the value of this n-stage repeated game behaves when n tends to infinity? And this is the first part of Aumann and Maschler's seminal K-view theorem. So to state it, let me first introduce the non-revealing game. So for every state, we define a zero-sum matrix game, GK, which simply fixes the first coordinate of the pair function G to be that state K, and we go over all pairs of actions available to players. And we denote by U of P the value of the zero-sum matrix game in which we take the weighted average of those matrices GK with respect to the probability distribution P. So if we denote by Vn of P the value of this game, their seminal theorem states that the limit as n tends to infinity exists, and moreover, it equals K-view of P, where K-view is defined from the simplex of probabilities over K to R, and it is the smallest concave function greater or equal to U. So here we see a simple example. To prove this result, Aumann and Maschler introduced many new techniques, one of which is the technique of splitting, which gives an exact recipe for player 1 as to how, when, and how much to use his information. So let me give a very short example. We look here at the graph of the function u of p, and we look at this point p. This is a point at which the graph attains a local minima. And let us assume that p can be written as a convex combination with weights alpha and 1 minus alpha of these two points pl and p right, so that the concavification of the function at point p just equals the same weighted average of the function u at the points p left and p right. So player 1 can perform an information-dependent lottery x, so that the posterior probability to the state k1 under x will just depend on the outcome of x. If x is left, the posterior will be p left, and so for the other case. And moreover, the distribution of the lottery x will follow the weights in the convex combination of p in terms of p left and p right. For the analysis of player 2, they introduced the notion of martingales of beliefs, used the minimax theorem, studied and defined the non-revealing game. And 40 years after Aumann and Maschler's seminal result, Renault looked at a more general problem from a dynamic standpoint, where he added an additional parameter to the model of Aumann and Maschler, and that is a stochastic matrix M over the state space K. So this is a matrix with non-negative entries, so that the elements in each row sum up to 1. And he once again considered an n-stage repeated game, this time depending both on the prior P and on the matrix M, in which we look at a stochastic process, an n-step stochastic process that follows the Markov chain with initial P and stochastic matrix M, so that at each stage, small n, player one is informed of the realized value of the Markov chain. Again, both players choose simultaneously actions, IN and JN, which are publicly announced, and the total payoff to player one will be once again the average per stage payoff, only that notice that this time at each stage, the state evolves stochastically according to the chain. A big difference between the models of Reynolds and Aumann and Maschler is the information that player one has to deal with. You can think of the information in the Aumann-Maschler model as being a static one, namely player one is informed at the start of the game of the chosen state, and that's it. He has nothing else to learn. Whereas in Reynolds' model, there is a constant stream of new information for player one that he has to take into account on the fly. And in 2008, Neyman was able to construct a beautiful reduction from this dynamic information to a more static information. And he did it using a tool from probability theory that sometimes is being referred to as a real-time transformation, where he changed the Markov chain to a closed process, which can be embedded in a more general model of Aumann and Maschler, in which the stage game are played in extensive form. Reynolds theorem, once again, the first part of it deals with the existence of the value of the limit of the n-stage values as n tends to infinity. And here again, this limit exists, and it equals the concavification of some function w, which corresponds to a new non-revealing game Reynolds defined and studied, evaluated at P times some stochastic matrix B0, where B0 can be attained as the limit of the transition matrix along some arithmetic progression of powers. And in this work, we want to maybe give a more general framework to the dynamics aspect. So we just fix a stochastic process psi. This is a discrete time process on some probability space, and we assume that its steps are supported on a finite set K. This set K will be the set of states of the game. And once more, I and J are the finite sets of actions available to players 1 and 2. And G is a scalar function that assigns to each state and pair of actions a payoff. Consider now the infinitely repeated game, which depends on this process. And this game will be played by steps. So at each stage n, player 1 will be told the current realized value of psi, that is psi n. Both players will continue by choosing actions in their own set of actions, which will be publicly announced. Okay, what will be the final duration payoff in this case? So as before, for every pair of strategies, sigma of player 1 and tau of player 2, we can look at the expected per stage payoff, where we take expected value over both the strategies and the process. And this game is a finite game in extensive form, so we can denote its value by Vn of psi. And an important asymptotic property that is studied in these infinitely repeated games is the notion of the uniform value. So this will be a scalar, and it will be said to be the uniform value of the game if two conditions hold. The first of which is that player 1 can guarantee it, namely for every epsilon, there exists some cutoff n epsilon and the strategy sigma epsilon, so that for every duration above this cutoff, player 1 can guarantee at least V infinity of psi minus epsilon against all strategies of player 2. And the dual condition for player 2 is that for every epsilon, there exists some strategy tau epsilon of player 2, and the cutoff, so that for every duration above this cutoff, the payoff at the game with this duration will not exceed this uniform value plus epsilon against all strategies of player 1. So let us now complete the theorems of Aumann, Maschler, and Reynolds. let psi of an be the Aumann-Maschler dynamics, namely every step of the process agrees with the first step. The seminal Cap-View theorem states that the uniform value exists and it equals to the limit of the values of the finite duration games and to Cap-View of P. And let psi of R be Reynolds dynamics, in which the process follows a Markov chain, and a parallel result holds as well. There exists a uniform value, it will equal to the limit of the finite duration game values. An important property that plays a key role in Aumann-Maschler is the stationarity. So this is actually a gift that this model allows. Let us assume that psi is some stationary process, which means that for every event A, which is Borel measurable under the product topology over the state space K, the distribution of the entire process is invariant to shift in times. And thus, if player 2 patches together with optimal strategies in the n stage game, and then in the m stage game, we will get the following inequality. The value of the m plus n stage game times m plus n will be non greater than n times vn plus m times vm. And the stationarity here allows this because player 2 can play whatever he wants, forget about everything he saw, and then play again optimally in some game, and the dynamics will start over. This implies that the sequence of scalars n times vn is subadditive, and by calculus we know that this guarantees that the limit of the finite duration games of their value exists. So we got it for free that this limit exists, and moreover player 2 can guarantee it by just patching together all of his finite duration games optimal strategies one after the other. One may ask thus, is it true that for every stationary dynamics, the uniform value should exist? And to start answering this question, we need to find some pool of stationary dynamics. And one of the biggest pools for such dynamics are measure-preserving systems. So let us consider the circle, the Borel sigma algebra on it, and Lebesgue's measure. And let us define the transformation T alpha to be the irrational rotation of the circle by the irrational degree alpha. So here we see the picture. And an important properties of this transformation is that, first of all, it is, of course, measurable. And the second property is that it preserves measure. This is actually a property of Lebesgue's measure, which holds in this case. And this is just an example of what is called the measure-preserving system. So in general, a measure-preserving system is a four-tuple. It consists of a probability space and some transformation from the space to itself, such that the inverse image of every measurable set is measurable, and the measure is saved under reverse images of the transformations. Let me give a further definition. This system will set to be ergodic if for every two events having positive probability, there exists some positive integer n, so that when we take A and intersect it with a shift in time n of B, we will get an event of positive probability. So an example of ergodic systems is the irrational rotation I just described, and to those of you who are familiar with it, the cut and stack system. Now, how can we get from these systems to a stochastic dynamics? So just we need to consider partitions of such systems. So here is a simple example. Let us look at the partition of the circle to the northern and southern hemisphere. And let us define now pointwise our sequence of random variables. So the first random variable will just indicate if the point is in the north or south. And for every n greater or equal to 2, the n steps of the process evaluated at x will indicate if after we rotate x n minus 1 times, we will end up in the north or the south. So here, x at the beginning is in the north, so the first step is 1. After we rotate it 3 times, we are in the south, so the fourth step of the process will equal 0. And this will be a stationary process. back to game theory, from player one's perspective, he just sees a binary sequence of realizations, and he believes that this point X was chosen from the circle randomly according to Lebesgue's measure. In the same fashion, we can consider any finite partition of such systems, measure preserving system, and we can define stationary processes that are generated by this partition by the following formula, which in word just means that the nth step of the process evaluated at X will equal J if and only if T n minus 1 of X will lie in the J's element of the partition. So this is just the parallel construction to what we see seen on the circle. And when player one observes this process, he learns something. So actually in the circle, he gets geometrical information. If he saw, say, the history 1 and 1, he knows that he is in this arc. And overall, there are 4 possibilities that he can know after 2 steps. After 3 steps, there are 6 information steps, sets that correspond to the different histories. And because alpha is irrational, then we actually know that for every n, there are exactly 2 n information sets, which become of arbitrary small measure as n goes to infinity. Okay, so these arcs become very, very small. Let us assume that some time in the process have go on, and we have here in. This is the information of player one after the n step. Let us define x to be the middle point of this arc, and rho to be the radius of this arc. And let me draw 2 danger zones near 0 and near half. And I call them danger zones because whenever the point x is in those zones, we know that at least 2 different points in the arc in would lie on opposite sides of the equator. So if all player one knows is that the true state of the world is in in, whenever x visits here, player one could not tell for certain whether he should see 0 or 1. This is not the case when the rotation puts us outside of the danger zones. Then player one will know that the L+1 step of the process will be constant on in. Yes, so it takes only the information in the n step, and it can already project very far to the future. And the question is, how often will x visit those danger zones under the rotation? And well, this is the ergodic theorem, that it will occur exactly at the measure of these 2 danger zones, which is 4 rho. And 4 rho itself will be a very small probability event as in will become smaller and smaller. So to summarize, whenever the information is refined enough, player one could predict more and more accurately into the infinite future, the steps of the process outside of some times in which he will be in the danger zones. So based on this definition, based on this observation, we defined the asymptotically predictable ergodic systems. And here I give only an informal definition. I'll spare you most of the details. So an ergodic system is asymptotically predictable if for nice and dense partitions in some sense, like say partitions to unions of arcs, the process that are generated by those partitions satisfy that if after n steps, the realizations at point x and at point y are close in some sense, agree most of the time, then the infinite realizations at point x and y will also be close for most of the time. And once again, 2 examples for such systems is the irrational rotation and the cut and stack, to those of you who know. Let's now fix a general partition of this system. This should not be a nice partition. It can be as general as you can think. We once again consider the stochastic process that is defined by this partition. So in the n step, once again, the process at point x will equal j. If when we take n-1 mappings of x, we will end up in the j's element of the partition. And for this process, I claim the following. In words, after observing the first capital N steps of Xi, I can predict with high probability, at least 1 minus epsilon, all future steps of Xi at an average success rate, which is high in it of itself, 1 minus epsilon. And formally, for every epsilon which is greater than 0, there exists some cutoff N and the sequence of random variables Y such that every step of the process Y is measurable with respect to the first capital N steps of the process Xi. And moreover, when we look at the event in which the lim inf of the frequency of times at which the two processes coincide, and we look at those points in which this quantity is greater than 1 minus epsilon, this event will have probability at least 1 minus epsilon. So this means that the prediction will be better and better with time. What does this mean for player 1? This means that the essential information to player 1 is in which one of the positive probability elements of the partition that generates the first small n steps of the process, the point that was chosen lies. So this is just as we've seen before, but this time we look after n steps. These are the possible information sets. And whenever player 1 is in one of those states, he knows pretty much what will happen in the entire future. So let us now recall that this is very similar to Aumann and Maschler, right? Because in their model, you learn an information and you know now from this point to infinity what will happen. The main difference is that the stream of states that follows this information set need not be constant. It can be very, very chaotic, especially in the irrational rotation system. And this is, of course, on one hand, good, because when we have finitely many information sets, we can split the beliefs of the opponent. But because this sequence is non-periodic, it is not clear what we can guarantee with the split. We don't have a closed formula, and we don't have a closed formula for the limit of the n-stage values as well, I mean, at face value. So we want to split, but we don't know whether it should equal the limit of Vn, and the limit of Vn only bounds the uniform value from above. So there is some work to be done to understand. But the main theorem of the paper, our main result, is that whenever we fix such an asymptotically predictable system, and we consider stationary processes generated by finite partitions of such systems, the uniform value must exist, and parallelly to the results of Aumann, Maschler, and Reynolds, it will equal the limit of the n-stage values. So a nice application of this result is a new limit theorem for such systems. So let us consider again an asymptotically predictable ergodic system, and let us take a partition of this system to two events and consider the binary stationary process generated by this partition. So we claim that there exists a triangular array T, such that two conditions hold. The first condition is that if we look at those information sets and we shift every one of them at the corresponding time described in the nth row of the array, we will get in their intersection a probability, an event of positive probability for every n. And the second property is that if we look at every row of this array and we look at the steps of the process evaluated at these times, and we take their average, their weighted average with respect to the probabilities of these information sets, then this will be a random variable, and it will go to the expected value of the process in L1. So to conclude the talk, let me just say that the general problem concerns the existence of the uniform value on measure-preserving ergodic systems. And thus far, we know that the existence holds in the Aumann-Maschler case, in Reynolds' case, and in our case. And of course, it is interesting whether it exists in other dynamics as well. This is it.
Thank you, Dima. We have some time for questions. I'm sure there are questions.
May I ask one more question? I'm sorry for you. You had a slide with an informal definition of predictability, and it had there you had an additional property. Yes, that was that they generate satisfy. So this capital N, what does it depend on exactly? Is it an epsilon type of definition for that for every epsilon you have an N? Or so it only depends on the epsilon and not on the observations until
No,
N, right?
it depends. It depends both on the epsilon. It depends on some measurand C, which bounds this difference between the two lines, and also N may depend on the process as well, on the partition.
Okay.
So, but this is very long and not so elegant definition.
Right. But the capital N doesn't depend on the values of psi at time 1, at time 2. You can say you know N beforehand. Okay. Thanks.
Any more questions?
Dima, do you mind me asking a question? Got it?
Yes, please.
Sure.
It's Arkady speaking, by the way. So thanks for your very interesting talk. If capital T is the backward shift, and X is some symbolic space, what kind of partition would be good for your theorem?
So we don't know. I mean, we cannot say almost anything about general systems, or if you call about Z, we can say almost anything about taking the transformation back in time. I mean, I presented only what is known to us.
Okay. Then thank you for this presentation. Thank you. Before we take the 15 minutes break, let me just thank GameNet for organizing it. Thank the chairs and the vice chairs of the different work groups for organizing it. And especially thank the speakers for these lovely presentations. We take now 15 minutes break, and then we reconvene in a special issue of the One World Mathematical Game Theory Seminar. So again, I wish to thank the young speakers. It's not easy to present, and it's especially not easy to present via Zoom. So thank you for accepting this special challenge. And thank everybody. I'll see you in 15 minutes.
Thank you, Galit, for putting this together.
Thanks, Galit.
Thank you.
Okay.
Stop the video. See
Okay.
you. Bye.
So hello, everybody. This is a special issue of One Word Mathematical Game Theory Seminar. It's a concluding talk of the GameNet Day. And for this talk, I'm happy and proud to say that we have with us Kostis Daskalakis. He's from EECS, CSAIL, and MIT, and this is just a list of affiliation. He works on computation theory, its interface with game theory, probability, statistics, machine learning, known for his research on computational complexity of Nash equilibrium. And well, I could try and read the list of prizes and awards, but that will give no time for the presentation itself. So I'm giving the floor to you, Kostis.
Thank you very much. It's a great pleasure to be here. So I'm going to talk about equilibrium computation and its relationships to the foundations of deep learning. And to motivate the talk, I'd like to consider the state of the progress of deep learning these days. So most of the impressive or promising applications of deep learning are about settings where a learning agent is consuming data from its environment. Sometimes these are IID data, or they could be affected by the choice that the agent makes in a stateful environment. But in any event, the agent is alone in an environment. The agent consumes data and makes decisions. Of course, the future of deep learning will involve not one, but two or multiple other agents that are all learning and interacting in the same environment. And of course, in that future, the learning and the decisions of the agent are going to be intertwining with the payoffs that they receive, as well as the changes in the state space. And so I claim that in that future, an agent who is learning and making decisions has to make those decisions in anticipation of the effects of those decisions in the experience of the other agents, what decisions they will make, how the environment will change as a result of that, and so on and so forth, which of course is an equilibrium learning and equilibrium computation problem. So and here's a thesis. So a thesis is that minimization is to current AI. As you know, a lot of the progress is driven by the ability of gradient-based methods to minimize complex learning objectives. Learning and making decisions in a fixed environment, while min-max optimization and equilibrium learning is the problem that an agent is facing when they're learning and making decisions in a changing environment, which could be changing because of the presence of another or multiple other agents who have conflicting or aligned interests. Could be caused by the presence of noise or adversaries, or poisoning or corrupting the data. Or it could arise indirectly. So sometimes the problem you're trying to solve is not itself a multi-agent problem, but introducing other agents is a way to enforce constraints in the same way that min-max optimization problems arise when you Lagrangeify a problem with constraints. So in all of these applications, we should be able to have general purpose methods to solve min-max or more generally equilibrium computation problems. And the challenge that, the empirical challenge is that gradient descent against gradient descent or against many other gradient descent procedures actually has a hard time converging to something meaningful or converging at all. And this is the topic that motivates the discussion today. So again, while in minimization problems, gradient descent converges at least to local optima, in min-max and more generally equilibrium computation problems, gradient descent does not converge. So it cycles or it's oscillating and it has hard time converging to anything. So let me show you a couple of pictures with the oscillations of machine learning. So again, just to fix notation, I will have a min-max optimization problem where X and Y range in some domain. And the gradient descent ascent dynamics arises by having the min player, so the X player, run gradient descents, while at the same time the Y player is doing gradient ascent. So the way I've written the dynamics here, this pertains to a situation where there are no constraints. If there are constraints, then you would have to project the updates onto the set, onto the constraint set. So as I've already said, running gradient descent ascent on in machine learning min-max problems is not well behaved. And here in the picture, I'm showing you what happens if you train a generative adversarial network on the data set called MNIST of handwritten digits. So I don't know if you're familiar with GANs, but GANs are a min-max formulation whose goal is to train a deep neural network that takes as input simple randomness like isotropic Gaussian samples, and in the output wants to produce complex samples. In this case, handwritten digits. So if you use gradient descent ascent to train a GAN on this data set, at different steps of the training, you see that the generator is producing gibberish looking digits as opposed to digits of numbers that are contained in this data set. And this is sort of like a min-max problem that is involving deep neural networks. So the function f is very non-convex, non-concave. But in fact, oscillations arise even in very trivial scenarios if you use gradient descent ascent. And the most trivial case is when you have this optimization problem. So you're minimizing over x in the reals, maximizing over y in the reals, this little function, x times y. So for this problem, the unique min-max equilibrium is the 0, point. Yet, if you run gradient descent ascent, which becomes this little update shown here, what you see is this going around and spiraling out of the equilibrium behavior. And that spiraling behavior is actually very generic. So for this, and here sort of like in the picture, I have pasted from a paper I wrote a few years ago on this problem. I've pasted what happens if you have a bilinear objective and you try various variants of gradient descent ascent. As you see in the picture, the details don't matter. You know, all sorts of weird tricks you can do to try to stabilize the dynamics actually don't work. So here, for example, I have here's the standard gradient descent ascent. Over here, I'm adding gradient penalty. So I don't want to let my gradients grow too large. Over here, I'm adding momentum to the dynamics. So momentum is a very useful tool in minimization problems, but momentum doesn't help over here, and so on and so forth. So here I'm showing a bunch of ways to modify gradient descent ascent dynamics that actually don't work even in this bilinear objective, which is convex concave and should be more well behaved. Indeed, a paper by Mertikopoulos, Papadimitri, and Piliras a few years ago shows that gradient descent ascent and actually a much bigger family of learning dynamics are not going to converge in min-max optimization problem, even for bilinear objectives. In other words, for a big class of dynamics called follow the regularized leader, you cannot fix the dynamics by choosing the regularizer cleverly. So while thinking about that problem a few years ago, we came to the realization, sort of like an obvious realization, that when you have dynamics that are spiraling away of the target, well, there's something wrong with the momentum. So zooming into this picture, okay, so over here again, this is for this problem, this is 0, 0, the equilibrium of this problem, and this is the spiraling behavior of the gradient descent ascent dynamics if you start from the purple point. So zooming into this picture, what happens is that at your starting point you get some gradient, and you move somewhere, and then over there you have another gradient, and the momentum is pushing you away from the target. So realizing that, then it makes sense to, rather than using positive momentum, which is what you want to do in minimization problems, to actually do negative, some form of negative momentum. So in that paper, we proposed using for GAN training and min-max optimization, what is called optimistic gradient descent ascent, where you undo a little bit of yesterday's gradient at every step of the dynamic. So at time t+1, rather than subtracting the gradient at time t from the current point, you also add the yesterday's gradient for x. And over here you subtract. This is the ascent player. You subtract. So you undo a little bit of the push that you showed yesterday. So in this picture over here, if I undo a little bit of, this is yesterday's gradient, this is today's gradient. If I undo a little bit of that, then I'm being pushed inside, and as you can show, this corrects the dynamics. So using some form of negative momentum has a long history in optimization, and more recently has been explored in the context of GAN training. So what do we know about negative momentum? There are two primary negative momentum methods in the literature: optimistic gradient descent ascent that I showed already, which is due to Popov from 1980, and extra gradient due to Korpelevich. So they are related, but the details of extra gradient, if you haven't seen it, don't matter for my presentation. But I'm just stating the existence of this method and the fact that a classical line of work has shown that these two methods, if you use them in a min-max problem where the objective function is convex in X and concave in Y, so von Neumann setting, you get a last iterate convergence of the dynamics. You don't get this cycling behavior around the equilibrium. You get that the last iterate of the dynamics converges to the target. And over the past, I don't know, couple years or so, there has been a renaissance of papers that try to understand this problem deeper and look at convergence rates to the equilibrium. And roughly speaking, we have a very good understanding of the rates that these methods experience in unconstrained problems, but we don't have a very good sense of how fast these methods converge in the constraint setting.
Can I ask a question?
So that is, yeah.
Yes. Somehow there is here under the rug a second derivative. Are there methods that work with the second derivative? of F?
The so certainly there are methods that work with second derivative, and indeed there have been methods proposed in this literature that work with second derivatives. So these works here don't use second derivative, like these two dynamics that you see here.
Does this one work in some way close or similar to the methods with second derivatives?
So yes and no. I mean, so first of all, let me put it this way. So I don't know how to derive these two methods by discretizing a continuous method that contains second derivatives. So I cannot, for example, like the plane gradient descent, you can certainly view as a discretization of the gradient flow dynamic. So x prime equals, eta gradient or minus eta gradient. So these two methods, I don't know how to derive by discretizing a continuous method. So it's not super clear to me, if these two methods are trying to implicitly do to use second derivatives, but there's certainly, an aspect of, at least, there is certainly an aspect of using, approximations to second order information.
Okay.
I'm going to come to the topic towards the end of my talk, a little bit later in the topic of second order. Yeah. But sort of like concluding this first segment of my talk, which was mostly focused on the motivation and the behavior of gradient descent and its variants on min-max problems with convex and concave objectives. The main open problem, if you, as a takeaway, is understanding better the rates that these methods or other methods experience in the constraint setting when the objective function is convex concave. And sort of like a comment on the previous question, typically we want to avoid running second order methods because our goal is to solve very high dimensional problems, and computing Hessians is something that we certainly want to avoid as a general comment on what one would like to shoot for in these types of settings. So that's an interesting open question that is being looked at intensely the past few years. But the major open question, which is more applicable to deep learning, is to get any positive result, last iterate or not, asymptotic or non-asymptotic, when f, the objective function, is not convex concave. And this is the main focus of my talk today. So I want to look at min-max problems where the objective function is not convex in x and concave in y. Okay. So I'm moving on to this main focus of my talk. So of course, when the function is not convex concave, von Neumann's theorem breaks. So there have been generalizations of von Neumann's theorem, but to quasi-convex, quasi-concave settings, for example, but these are not the types of settings that are of interest in deep learning applications. So when min-max theorem breaks, for some objective functions, the min-max is different than the max-min. In other settings, equality holds, but there are multiple and disconnected solutions, as you see in the pictures here. Okay, so for example, in this picture, you have that min-max is different than max-min, if you think about it, which sort of says that the sequence of moves plays a role in this case. So what should even be the goal when von Neumann's theorem breaks? So let me discuss a few solution concepts that have been proposed in the literature. And I'm slightly going to generalize my setting now. So I have a function f that is continuous and convex. Sorry, that is continuous. And I'm going to have a constraint set that is convex and compact. And I'm going to be looking at the problem mean over min max of fxy when x and y are in the set S. So here is a little helper for the definitions that I'm going to state below. So when I say S is the constraint set. If I say S and a fix of x, I mean all the y's that accompanied by x belong in the feasible set. When I have S subscript x, what I mean, all the x's for which there exists an accompanying y so that they're in the set. So this is some like projection to the x coordinate of this set S. And similarly define these two sets. So here are some solution concepts that have been proposed in the literature for when f is not convex concave. The first one is a local mean global max solution. Right, so and it's defined as follows. It's a sequential notion, and it's defined in the following way. So a point x star y star that is feasible is a local mean global max solution if for some delta bigger than 0, the function value at this point x star y star cannot, so for a local deviation of y, sorry, for a global, so if y plays the best response to x star, so for any y in this set, the function value cannot increase. So the y player is globally happy. So the y player has no global move. That's why it's called global max. The y player has no global move that improves their payoff. And it's a local mean because the x player has no local move. So the x player is looking at a neighborhood of x star intersected with feasible x's. And they don't want to be able to improve. But what is an improvement for the outer player? An improvement for the outer player is when you move to that x and you let the inner player best respond globally, that's your anticipated reward if you make a move to x. So point is a local mean global max solution if y star is a global best response to x star, and there is no local move of x, so that after y best response, that decreases the function for x, for the x player. So that is a local global max solution, and it x global max with respect to y, and I'm respecting the sequentiality of this min-max problem.
Sorry.
Of course, for the purpose. Yeah. Yeah.
The assumption here is that f is convex, like continuous and convex.
No, sorry. So it is f is continuous.
Okay,
and this
so
set S is convex and compact.
Convex and compact. Okay. Sorry.
Yeah. So this is a reasonable solution concept, but the bad feature about it is that I'm considering global moves of the y player. So in a high dimensional space where f is not convex in y, this is a tall order to be able to guarantee such a thing. It's going to be NP hard. So the relaxation proposed by Jean Trapali and Jordan is the local min, local max version of this solution, which they call local minimax. So you keep that x is considering local moves and anticipates the responses of the y player, but you're only considering local moves of the y player. I'm not writing down the equations to avoid confusing you, but this is what it is. Okay, it's a local min, local max solution. So in prior work with Panagias and in work by Mazudmar and Ratliff, they proposed the non-sequential version, the simultaneous version of local min, local max, which we call local min max equilibrium. And this is, as you may anticipate, is a point x star y star that's feasible and such that no local move of x can improve for x, and no local move for y can improve for y. So that's a simultaneous solution concept. Now, so again, 1 and 2 are sequential notions. And this is fully local. This is a simultaneous notion that is fully local. Now, should we be happy with our solution concepts? Well, not too happy, because while 1 is guaranteed to exist, 2 but it's too strong, it's NP hard, as I already mentioned, 2 and 3 are not guaranteed to exist. So 1 always exists, but it's NP hard, but 2 and 3 do not always exist. So this is the first attempt at relaxing the global min, global max solution. So we got existence for this guy, but it has some global optimization in it, and it becomes NP hard. And these two purely local solutions, unfortunately, are not guaranteed to exist. So the other thing that if you're quick, you have realized, so it's actually typically confusing to think about the definitions, but as it turns out, the simultaneous is actually a subset of the sequential local min, local max solution. But as I said, these two might be empty. Now, here's another solution concept that is reasonable to define. And that one is going to be one that always exists. It's going to contain the simultaneous local min, local max. It's going to be broader. And this one is a fixed point of the natural dynamics to solve this problem. So the natural dynamics is the gradient descent ascent projected on the feasible set, which is written here. Of course, a fixed point of this guy is guaranteed to exist, because this is, if the function f is smooth, okay, so I'm going to assume that assumption as well. So it has continuous gradients. As it turns out, this is continuous, and this is guaranteed to exist. Okay, so this is what I'm writing here. So this is guaranteed to exist if f is continuously differentiable. Now, right, so what is slightly weird about the way my shapes look like over here is that it appears sort of obvious that, natural at least, or intuitive, that the fixed points of GDA really capture local min-max solutions, because, this dynamic here says, it says that, if I try to locally improve X, I arrive at the same point. And if I locally try to improve Y, I arrive at the same point. So it's kind of weird that I'm plotting the red thing here bigger than this. And I have to, because as I said, this does not always exist. Well, this is guaranteed to exist by Brouwer's fixed point theorem. So what is this weird discrepancy between this solution concept and this solution concept, given that this is really looking at local deviations of the X player and the Y player, and is trying to, essentially the fixed points say that these such deviations don't exist. So what is this weird discrepancy between them? So it is natural to think that the discrepancy is due to potential unstable fixed points of the gradient descent dynamics, which are not locally minimax. But this is not the reason for the discrepancy. In fact, we already have seen that there are min-max solutions that are not stable for the gradient descent ascent dynamics. My very first example was this simple example where 0, 0 was an equilibrium, but GDA was unstable. If you started it close to the fixed point, it actually spiraled away from it. So certainly there are min-max equilibria that are not stable for the GDA dynamics. And you can show the opposite. You can construct functions where GDA dynamics actually has stable fixed points that are not min-max. So let me not get into those details, but stability is not the reason why these two are different. What I claim, and I'm going to show you in a bit, is that approximation is what makes these two things different and can explain their difference. And here's what happens if I relax my local min, local max equilibrium notion. So now I'm relaxing the constraints that I wrote earlier. I want that locally y cannot improve by more than epsilon. And I want that locally x cannot improve by more than epsilon. And here's the interesting things that happen once you start considering approximations. I'm going to call G the Lipschitz constant of f, and I'm going to call L the Lipschitz constant of the gradient of f. So with G and L, as well as epsilon and delta parameters of my problem, here's the nice picture that arises as I go from very local, small delta, to very global, large delta considerations. So the existence of the problem, the behavior changes. So below a certain threshold, so if delta is very, very local in comparison to epsilon and the Lipschitzness of f, the problem is trivial. So everything in my domain, every feasible point is actually a local min-max solution. If I consider very global, if I have very global considerations, these equilibria may not exist and they're NP hard to compute. Indeed, if delta is comparable to the domain size, of course, now the x and the y player have global considerations. And if my function isn't convex or concave in y and x and y respectively, of course, the problem is naturally expected to be NP hard. But here's an interesting, nice regime that I think is an interesting one. When delta is not too large and is not too small. So below a certain threshold, epsilon delta local min-max equilibria are guaranteed to exist. And they're actually equivalent computationally to fixed points of GDA. So if delta is related to epsilon and the smoothness L of the function in this way is below this threshold, then I claim epsilon delta local min-max equilibria exists, and also computationally finding such equilibria is equivalent to fixed points of the gradient descent ascent method, which is another reasonable solution concept for our problem. So I guess what I'm saying is that in the local regime, these two reasonable relaxations of finding global min-max points are computational equivalent, and this will be my focus here. Of course, whether these solution concepts make sense at all really depends on your problem. So whether that's a good compromise, looking for local min-max solutions, approximate local min-max solutions, or approximate fixed points of GDA, is really a matter of your underlying problem. So indeed, from a game theoretic standpoint, a very interesting question is, what are other reasonable solution concepts that exist and have some hope of being computable, either ideal in polynomial time or at least have asymptotic methods converging to them. So for the rest of my talk, I'm going to consider this notion of approximate fixed points of GDA or equivalently approximate local min-max equilibria.
May I ask a question?
Yeah.
Yes.
Yeah.
An alternative view would be to say in this type of game, there always exists a value in mixed strategies. Okay, if you allow players to play randomly, you have the value.
Right.
And then maybe you could try to do some gradient descent ascent in space of probabilities, maybe in Wasserstein space or thing like this. So this makes sense for sure. Is it tractable? Is it known? Or?
Right. Yeah, so that is a very reasonable reaction to what I'm talking about. In practice, this is not a reasonable approach for deep learning. So imagine, like X and Y are very high dimensional real vectors. So now maintaining probability distributions in those spaces is not a very practical thing to do. If you can prove that your mixed equilibria have a very small support, you could consider such solution concepts. But you would have to prove something like that either the equilibria have small support, or at least that there is a succinct representation of the mixed equilibrium that can be sampled. So if that's certainly an interesting direction to consider, but you would have to satisfy some constraint of that type.
Mm-hmm. Because the payoff of the F value of your approximate fixed points may be very different from the value of the game in mixed strategy.
That's right, yeah.
Okay.
So again, I wanna consider now this local notion, local min-max notion, and I was saying in the beginning that like a lot of the success of deep learning has been based on the success of gradient descent in finding local minima. And I want to understand, really the question that I'm asking now is like, if I'm gonna base multi-agent deep learning on gradient descent, do I have any hope of doing that? So really, I'm interested in a comparison between minimization, where I have seen a lot of successes, and min-max optimization, where we haven't. So I want to make a little comparison between minimization and min-max optimization. So for my comparison, I'm going to have, okay, so this is a funny way to write a minimization problem. So I have X and Y, but really I'm minimizing with respect to both, and they belong in a feasible set. Over here, I have a min-max problem like the ones I've been talking about so far. So for my comparison, F is going to be Lipschitz and smooth, but it's not going to necessarily be convex for the left-hand side, and convex in X, concave in Y for the right-hand side. My constraint set in both cases is going to be convex and compact. And I want to make a comparison between these two problems. And I'm reminding you that I'm going to be looking at epsilon delta approximate local equilibria, which again is on the right-hand side. I don't want to be there to be a local deviation of Y that improves by more than epsilon, and local deviation of X that improves by more than epsilon. Over here, both players are minimizing, so I don't know, like this is just a weird, like, yeah, this is really one variable, and I don't want them to be there to be. This is just a funny way to write a minimization problem, but I don't want there to be a joint move of X and Y locally that improves. Okay. Okay. So now the point is that this guy, left-hand side, exists for every delta, but it's NP hard for large deltas. This guy exists for small enough delta, and it's equivalent, as I said, to GDA fixed points. So how do these problems compare? The easy comparison is when F is convex over here, and it's convex concave over here. In these nice regimes of the problem, there is no real difference between what optimization methods can do for this problem and for that problem. Namely, gradient-based methods in both cases can find approximate local solutions in both cases after poly 1 over epsilon and smoothness steps. times some factor that depends on the diameter of the set or something like that. On the other hand, so there's no real difference between the problems. So these are nicely behaved settings for both problems. On the other hand, if I turn this F to be not, I don't ask convexity over here. Not big, I don't encounter a big problem, at least in the local regime. In the local regime, this problem remains tractable. Okay, again, as I said earlier, if delta is too large, it's NP hard, but in the local regime, this problem remains tractable and the number of steps is the same as before. So minimization problems don't really care, at least for as far as local approximate equilibria are concerned, they don't really care about whether your function is convex or your function is whatever, as long as it's smooth. The problem that this talk is focusing on is what happens in this scenario. F is not guaranteed to be convex concave, but only smoothness, only ellipses and smooth. And I'm trying to solve this min-max problem. So the main result of our work is the following, that now there is a big difference between minimization and min-max optimization. So for min-max problems with non-convex concave objectives, first order methods require exponentially many steps in at least one of the relevant parameters of the problem to find approximate local min-max equilibria in the local regime. So the problems deviate outside of their benign regimes. So minimization is still well behaved if your goal is to find local minima. Min-max problems become much harder. They become harder. So they require exponentially many steps, at least first order methods, to find local min-max equilibria in the regime where these exist. In fact, this exponential lower bound on the number of queries that you have to make to the function f is a byproduct of a deeper result that says that computing min-max equilibrium in this regime is actually PPD complete. So it's actually a byproduct of our hardness reduction to prove that this problem is PPD complete, to show that an exponential number of queries to the function and its gradient are needed by first order methods. So in particular, this result says that any algorithm, not just first order, second order, whatever, any algorithm needs to take super polynomial number of steps unless PPD collapses to P, polynomial time.
Can I ask a question on the previous slide?
Yeah.
Can you go back to the previous slide? You say in a...
This slide?
No, the next one. When you say in at least...
Yeah.
You say that it needs exponentially many steps in at least one of, and you list the number of variables.
Right? Yeah.
What happens if some of them are fixed?
So I haven't proven that yet. So I guess just to clarify this a little more, if basically what we show a hardness result when all of them are polynomial in the dimension. So we come up with a function f where the ellipsisness and the smoothness as well as the approximation that we ask are all polynomial in the dimension. And we prove that this instance requires exponentially many queries in the dimension.
Mm-hmm.
So we don't know, for example, what happens for different trade-offs yet.
Okay.
That's a great question. Yeah, so that's a great question.
Can I ask a question as well?
Yeah.
So what is the domain here? Is it a hypercube? Is it a simplex? Do you think that this matters?
We show this result when S is a subset of the hypercube. It's a polytope. It is a subset of the hypercube. It's a stripe where X and Y have to be close to each other. So it's a stripe that asks X and Y to be L infinity close to each other.
Okay, and is it interesting from an
So it's an open question.
Yeah. Sorry, go.
Yeah. Yeah, it's an open. Yeah, sorry. It's an open question whether we can prove this result when X and Y are not constrained together, but they're a product constraint.
I see. Thank you. And is it interesting from an application point of view to consider settings where X and Y are constrained into simplices and some of the other constraints are bounded or not?
Sure. I mean, it really depends on the applications that you have. Yeah.
Okay, thank you.
Yeah. Right. So I guess just to summarize, the results I'm showing you here are enough to say that min-max is much harder than min, and in particular, while this one has polynomial number of steps in these two parameters, this one needs exponentially many steps. You cannot replicate this result in this setting. All right, so that is the main result. Let me try to sketch a few ideas for the proof. So again, what are my problems and my questions and my results? So I want to understand the complexity of local min-max optimization. And I'm considering two problems. One is for epsilon and delta in the local regime, so below this threshold where solutions exist. And given some function f, I want to compute a local min-max equilibrium. This problem is finding a fixed point of projected gradient descent ascent, an approximate one. And as which is shown here, I have already argued that these two problems are, I haven't argued, but I claimed these are a computational equivalent. So in particular, yeah, so I can focus on either one of them. All right. Now, so what is the complexity of those? I've already said it's PPD complete. Let me talk a little bit about why it is not NP hard. So for F that is arbitrary, these problems seem very difficult, but you are familiar at all with the complexity of computing equilibria or Brouwer fixed points, you probably have already seen that by work that was done in the 80s, that they cannot be NP hard unless certain complexity theoretic collapses happen in the in particular NP equals co-NP, and that the right method to carry such problems with guaranteed solutions is through the complexity of total FNP. And maybe you have seen this picture that sort of like PPD lies between P and NP complete problems, and it captures the complexity of computing Brouwer fixed points and Nash equilibria, as well as several other problems in topology, such as Sperner's lemma. So, and because GDA fixed points and equivalently local min-max equilibria are special cases of Brouwer's fixed point, of course, these solutions have to lie somewhere between P and PPAD. They cannot be harder than PPAD because they are fixed point problems. So, so what we show is that they don't lie sort of like in between. That what we show is that they're actually equivalent to PPAD. Now, I'm not sure if you're familiar with PPAD, and I don't have time to define it. properly. But PPD is a class, a complexity class that was defined by Papadimitri in '94. And it captures problems that always have solutions, like Brouwer's fixed point computation or Nash equilibrium computation. And it captures those problems with guaranteed solution where the proof that the solution exists is by this graph theoretic parity argument that says that if a directed graph has an unbalanced vertex and vertex where the in and the out degree are different, then it must have another unbalanced vertex. As it turns out, this very trivial looking parity argument lies in the heart of the existence proof of many problems in many things. Indeed, using this parity argument, you can prove Sperner's lemma, which you can use to prove Brouwer's fixed point theorem, which you can use to prove Nash's theorem. So, which says that all these problems, Sperner, Brouwer, and Nash, they're all inside this class, this complexity class. And work that I and others did back, maybe 10 years ago or so, have shown that not only those problems are in this class PPD, but in fact they are complete for the class PPD. That is, that PPD, this parity argument, the complexity of finding unbalanced vertices in a directed graph like that, exactly captures the complexity of computing these interesting problems. Okay, so I guess, again, what I'm saying here is that in the heart of Sperner and Brouwer and Nash existence theorems, what happens is that you can define a huge graph, G, that is directed, and you can point to a special unbalanced vertex of that huge graph. And the computational problem that arises is to find another unbalanced vertex. And if you do, you would be able to compute a Sperner solution or a Brouwer fixed point or a Nash equilibrium. So this is what takes place in the heart of these problems. And again, what we show is that finding GDA fixed points is PPD complete. So in particular, exactly as hard as finding general Brouwer fixed points, exactly as hard as computing equilibria in general games, even though these things are zero-sum games, and any problem in PPD. And again, so the oracular bound is just a byproduct of this result.
Can I have a question, not about your talk, but on something that you quote just for our education?
Yeah.
In the previous slide, you had quantified it for two-player games.
Yeah.
And the top result, is for 2-dimension. Is the 2D?
Sorry. Yeah, sorry. Yeah, sorry. Let me explain what I'm saying here. I went too fast. So Papadimitri showed that Sperner and Brouwer are PPD complete for any dimension above 3. And then Chen and Deg in 2005 proved, so from a computational standpoint, the smaller the dimension, the easier the problem becomes. So Papadimitri showed that these problems are hard if the dimension is at least 3. What this guy showed is that it's also hard even if the dimension is 2. So in 1D is actually a trivial problem. So 1D trivial, and then above 2 dimensions, and Sperner are PPD complete. Similarly, our first result in 2006 showed that for at least 4-player games, and then after 3-player games, Nash is also PPD complete. And then Chen and Deg showed that even for 2-player games, it's PPD complete. And of course,
So this is from the side of the hardness. Hello?
Abraham, okay.
Hi, sorry.
I lost the slide.
I briefly left the Zoom, but I'm back.
Okay, so what I try to understand is the relation between this graph figure that you mentioned with the ingoing and outgoing. Is this relevant for the two-dimensional cases or for any dimensional case?
So for any dimension, So I claim that you can prove Brouwer's theorem, Sperner's lemma, by defining a graph that is directed, and it has in degree and out degree 1. So in particular, it's a bunch of paths, directed cycles, and isolated vertices. So that if you find any node of degree 1, so any unbalanced node, you would be finding a Sperner solution.
Mm-hmm. Okay.
If I had time, I would show you the proof, but it's I would need more. Like I think I should end soon, so I don't have. But sort of like, I mean, like I don't know if you've seen the proof of Sperner's lemma, but it kind of like looks something like this, right? So you
I
like
have seen
Sperner's
it.
lemma says that sort of like
I have seen it and I'm proving it, but in classes. But my question is, if there is a simple proof with such a graph, I may use that in teaching. So that's my wondering.
Yeah. So there is a simple proof with there is a very simple proof using graph theory. When should I end? Am I ending in 1 minute, or what is? I'm confused about the time that I have.
Don't be confused. You have a few minutes, but then we can start a discussion that is not that is very flexible. So.
Okay. So I mean, I could, if you would like. I mean, I don't have any much to say. I would just conclude it now, but I can show you the proof of Sperner's lemma to relate it to PPAD, if that would help the discussion after.
Yeah, my question is it different from the type of proofs of path following arguments that were running in the 60s? I think Wilson might have even been involved.
That's exactly what it is.
Okay.
Path following, like SCARF.
Yes, SCARF, and I think also Wilson was involved in it. Yes.
Right. Yeah. So Wilson. Yeah. All these like Lemkehausen, that type of work.
Mm-hmm.
Right.
Okay.
Except I guess what I'm. Yeah. So like I guess what I was saying with this slide here. If I'm able to ever find it, is that sort of like, if you look inside those proofs, like the existence of the solution is really boils down to this trivial claim. So everything else is building a proof around this graph theoretic lemma, but like the heart of why the object exists is really this, what you see here. Mm-hmm. Everything else is just mathematical kind of like wrapping. But this is really the heart of what explains the existence of solutions. And for this reason, you can capitalize on that and define a complexity class out of this lemma. And successfully, this class captures exactly, not more, but exactly the complexity of computing these problems.
Mm-hmm. Okay, right? Thank you.
I mean, yeah. I mean, okay, so I don't have much to say, more to say. So let me actually show the Sperner's lemma, because I have been a bit abstract in my discussion of PPAD. Let me just show it and connect it to directed graphs, and then I'm going to stop to open it for more questions. So here's Sperner's lemma. Again, you can use Sperner's lemma to prove Brouwer, and you can prove Brouwer to prove Nash. Okay, so so the existence of Brouwer and Nash can be explained by this lemma, and computationally as well. If you're able to solve the computational problem that is motivated by Sperner's lemma, you can also solve efficiently Brouwer and Nash. So what is Sperner's lemma? If you haven't seen it, you have a grid in 2 dimensions or many dimensions. I'm going to show you the 2-dimensional version. you color the grid with in 2 dimensions with three colors, in 3 dimensions with 4 colors, etc. So you color it with 3 colors in whatever way you want, but you have to respect some boundary coloring conditions. And here I'm showing you a simple coloring condition that works. So suppose you color this grid with 3 colors, but the boundary condition satisfies what you see here. So this is all red except this guy. This is all blue except this guy. This is all yellow except this guy. Otherwise, you're allowed to put any colors you want in the middle. So Sperner's lemma says that no matter how you color the internal vertices, there is an odd number. So in particular, at least one trichromatic triangle. So a triangle with all the 3 colors. So an odd number of them. So at least 1, 3, 5, etc. And over here, you see 5 triangles that satisfy this property. Now, I claim that to prove this theorem, it boils down to a parity argument like the one I talked about earlier. And here's the simple proof that you can use to prove the existence of an odd number of trichromatic triangles. So what you do is you define a walk. You start at this bottom left triangle. And what you do in your walk is you look for red, yellow doors and try to cross those doors. So in fact, this triangle, the 3 pillars in this, so this is think of it as a big factory with triangular rooms. Every triangular room has 3 pillars. This room where you start, the 3 pillars of that room touch the boundary. So the 3 pillars are not affected by whatever coloring you put in the middle, because these are boundary vertices. So you know, in fact, in particular, exactly how this room is colored. And you know that it has 2 red, yellow doors and 1 red, red door. What you will do is to cross a red, yellow door having yellow on your left. And even though there are 2 doors you can cross, 2 red, yellow doors, there's only 1 that you can cross with yellow on your left. So this is what you do. You enter into a new room through a red, yellow door, and you look at the color of the other pillar. If the color of the other pillar is blue, you stop because you entered into the room through a red, yellow door and you found blue. So that room has 3 colors. If the pillar, though, is not blue, it's either red or it is yellow. That means that there is another red, yellow door that you can cross. And you keep doing that until you stop. And you can prove that you will stop at a trichromatic triangle. I'm not going to prove that you will stop at this point because I will prove it at a later point. But this is what you do. So you cross red, yellow doors until you cannot move anymore. Notice that you will never exit the factory because there is no red, yellow door on the factory that you can cross having yellow on your left. So certainly, whatever work you will be doing, you will stay inside the factory. So you have to stay in the factory, and the only stopping condition is if you enter into a room through a red, yellow door and you find a blue. So the only question that is pertinent now is whether you will ever stop, because if you stop, certainly you stop at the trichromatic triangle, but maybe you won't stop. But what might prevent you from stopping? What might prevent you from stopping is maybe you do a little walk and then you feed into yourself and then keep going around the cycle forever. So maybe you form a row shape and you go around that forever. But for you to sort of like walk a little bit and then cross into your own path, the point of the crossing must be a room with 3 red, yellow doors. And that's impossible. You cannot have a triangle with 3 red, yellow doors. So your walk cannot exit. The only stopping condition is if you find a trichromatic triangle. And you cannot do a row shape and go around the circle of the row forever. So you have to stop. And the only stopping condition is you find a trichromatic triangle. So that proves that there is at least 1. To show that there is an odd number of trichromatic triangles, after this first walk settles, you can repeat this experiment starting from other vertices, from other triangles. So for example, you can start from this triangle. This triangle has actually 2 red, yellow doors, but only 1 that you can cross having yellow on your left. So you cross that and keep going, and surprise, you found a trichromatic triangle. then you can go backwards from this point. So so that yellow is on your left. And here you find another trigonometric triangle. You can try to do this experiment from any starting point. And this will actually cover your factory with paths, circles, and isolated triangles. These triangles have no red yellow doors. So if you start here, you don't move. So abstractly, what happens in this proof is that if this is the set of triangles, what you do is you define a transition rule from triangle to triangle, from a triangle to a neighboring triangle. And the transition rule is that if these two triangles share a red-yellow door, you can go from 1 to 2 if crossing that door, you have yellow on your left. So with this transition rule, what you did effectively is you defined a directed graph. So the vertices of the graph are the triangles of the factory. The directed edges are like defined by the transition rule. And the result of that is that all the vertices of the graph have in and out degree at most 1, because if you think about it, however you color a triangle, it can have at most 1 red-yellow door that you can exit having yellow on your left, and you can have at most 1 red-yellow door that you can enter into that triangle with yellow on your left. So the transition rule defines a directed graph whose vertices are the triangles and which has in and out degree at most 1. In fact, the degree 1 vertices must be trichromatic. Degree 1 vertices must have a red-yellow door that you either enter or exit from those triangles, but not another one. The only way you can have a triangle with exactly 1 red-yellow door is if it's trichromatic. The only way you can have a triangle with 2 doors that are red-yellow is if it does not have blue. And all other triangles are degree 0. So effectively, the graph looks as follows. So you have, this path that you started from the bottom left triangle that has to end somewhere. And you have a bunch of other paths and cycles and other isolated vertices. And the fact that there is always a starting point, there is always a starting path, proves the existence of a trichromatic triangle, because this path has to have another endpoint. A graph with in and out degree at most 1, it's a bunch of paths and cycles and isolated vertices. And as I said here, all the degree 1 vertices, so all endpoints of paths, must be trichromatic, except for this one over here. And that proves the fact that there is an odd number of trichromatic ones. So that is basically the proof of Sperner's lemma through graph theory. So you define a graph between triangles, and the way you define your graph, all endpoints of paths must be trichromatic, except the very special one that starts at the bottom left. And that's the end of the proof. So this is why Sperner's lemma is actually due to this parity argument on directed graphs.
One is to make a comment that most of the wording was tailored for 2-dimension, and one can extend it to more dimension, but the wording should be much more careful.
Yeah, so for high dimensions, I'm going to have a hypercube. I'm going to have simplices rather than triangles. I'm going to have dimension plus 1 colors, and I'm going to cross from one simplex to another if they share a facet, and that facet contains all but 1 special color. And the stopping condition will be I'm crossing into a new simplex, and the facet that I'm crossing has all the colors except the D plus first one. If the other one is the D plus first, I'm done because I found a panchromatic simplex. If it's not, then there must be another facet that I can cross to go into another simplex. So that
but also you have to take care of the issue that you said with the yellow on the left. Yes, this is another issue that you have to take care of.
Oh yeah, so you're right. Yes. Yeah, so you have to find, exactly. You're right. You have to define orientations of the facets and use those orientations. That's exactly right. Yeah, and that becomes a bit messy. So in class, I usually only give the 2-dimensional unless I need to spend many lectures.
Yes.
Yeah, you're exactly right.
I give the n-dimensional. I give in class the n-dimensional case for the simple reason that over the years, I have learned that a few that even turned out to be outstanding mathematicians misunderstood the Bauer fixed point theorem because they think that they could extend immediately the two-dimensional proof to n dimension. And usually when you ask them how to do it, you see that they are failing.
Well, it seems like we are kind of
so
moving through the discussion.
Yeah.
So let's just thank you first officially. Thank you. Thank you.
Thank you. Thanks.
And we can now open the discussion for more participants. If people want to ask further questions, now is an excellent time to do so.
So let me, if I may, maybe that's a good seat for the discussion, and with a philosophical corollary, which I already mentioned, but sort of like deep learning has been based on the fact that gradient descent is very successful as neural networks if you have enough data and you have supercomputers. But sort of like the type of stuff I've been talking about today is that this will fail in the multi-agent setting. And for this reason, I think game theory is important because the modeling, so like coming up with the right solution concepts, coming up with the right models of what multi-agent problem you're trying to are all.
I think we lost Kostis. Or is the problem only on my side?
No.
Oh, we lost him, actually.
We lost him, yes.
Just on the climax.
It's a cliffhanger, yeah. Well,
Yeah, yeah, he did it on purpose, you see, to heighten the degree of anticipation even more.
Okay.
Oh, and
he dropped.
In any case, I have to leave. So if he comes back, my thanks to him for a nice talk. Thank you. And for the organizers for picking the talk.
See you, everyone. Bye-bye.
Bye.
Salut, Jérôme. Salut, Pana. À bientôt. Bye.
Ciao, Sylvain. Salut.
See you.
It's good to see you all. Hi, Sylvain.
Hello.
I believe, though, he will reconnect, no?
I will wait.
Yeah.
Okay. See you. Bye. See you soon.
Kind of cute when somebody says in the talk, hello, and you see the chat and you think it's for you, but it's to everybody. So you.
Well, Bernard, I was intending to reply to Jérôme, actually to Jérôme's question about mixing equilibria, and I ended up replying to everyone. So there's that as well.
Marco has a cool background, Marcus Casini.
Change. So what do? We expect him to reconnect?
I mean, internet fails even at MIT, eh?
He might have to reboot and it takes a while, but then he might be back.
Hi, I'm back. Sorry.
Exactly.
Hi.
There you are.
So yeah, sorry. This is the first day of lockdown in Greece, and all the networks are overloaded.
Oh.
Yeah. So yes, yeah, I'm happy to take any questions if you
But we missed the coda to your last slide.
The which one?
The philosophical corollary. We missed completely.
Oh yeah. Yeah. Yes. Yeah. So I don't know if yeah. Yeah. So I can. It's a very simple one. So I guess so. My point is that deep learning, the success of deep learning was due to the fact that you can write down very rich models, and you can optimize them fairly well using gradient descent. And in view of sort of like the results that I talked about, the complexity results, you cannot approach
Oh, not again.
No, we'll never hear.
Yeah, sorry, I'm back. So I don't know what's going on. You cannot approach, I'm saying you cannot approach multi-agent learning in the same way because the modeling is very important. So the choosing the solution concept, writing down a model about what the agents know is very important. And importantly, you have to use intuition about the problem to be able to compute equilibria. For example, in AlphaGo, it's not like people wrote down very complex models for how to play Go, and then they just run a gradient descent to use to optimize them. They actually did use a lot of game theoretic understanding, like the min-max tree algorithm. So I guess my perspective on the future of deep learning in multi-agent settings involves a lot more modeling and understanding of the underlying game theoretic applications.
Okay,
you cannot
thank
just
you.
blindly optimize, is my point. Yep.
Ask another question, maybe?
Yeah.
Yeah, thanks for the talk. So I have the feeling that what you presented, everything was symmetric in X and Y. So it is min-max. Min-max is not equal to max-min, but what you do when you do the algorithm, you treat the two players exactly the same. Whereas in some cases, in learning, for instance, in GANs, I have the feeling that people are not really interested in the symmetric case. We really want to compute min-max because you have player X and he wants to find a robust solution to something. So they don't use the same gradient ascent, but they have different parameters. Eta is not the same for every player. So in which case of deep learning, you have an example where it's really symmetric. You need the two players and you need to treat them symmetrically. Do you have any ideas?
Right. Yeah, of course. So first of all, everything I talked about holds for the sequential notion. So the hardness results you cannot avoid for the sequential notion. The second thing to say is that sort of like the reason why people in GANs use different parameters for the two optimizers is precisely for the reason that otherwise the problem is very unstable. So one way to fix the oscillations is to, for every step of the outer player, to have the inner player do many steps.
Yeah.
And that tends to improve the oscillations, yet does not remove them, as I showed in one of the very first slides. Like in my talk, actually, one of the panels was actually doing exactly that, having like 10 steps of the inner player for every one step of the other player. So it decreases the oscillations, but does not remove them. So that's the second point. The third point is, yeah, so when do I anticipate using a symmetric notion? Well, I think these are the most applications. So so in the multi-agent setting, people are people, right? So the rational agents that are learning and making decisions. So if you think like sort of like GANs are really like what the little comment I made that sort of like the inner player is really like one that's controlling Lagrangian coefficients to enforce certain constraints. So really like in GANs, the inner player is sort of like a Lagrangian player, but like in most of the applications that I anticipate in the future, where I create my learning agent, my robot, and I launch it in the world, and you launch your own robot, and so on and so forth, the role of the players is more symmetric there. So I can see both types of applications. In terms of complexity, nothing changes much. The problem, the sequential problem is also PPD complete.
Okay, thanks.
Kostis, I have a question on this oscillation. So thanks for the nice talk, by the way. Really, I mean, but did you also use this negative step of the second to last step in order to dampen your oscillation? You know what I mean?
So for the for the lower bound, you mean? So for the
you showed in the beginning something where you said that the oscillation didn't. You always had this oscillation, even when you had a negative momentum.
So that depends. So if you have a convex concave problem and you use negative momentum, there are many ways to do that. But for convex concave problems, you have convergence. And this is very well established. So even for constraint settings, the only question that is open there is to prove rates. So rates for negative momentum are only known for unconstrained problems. There are a few cases where rates are known. I mean, rates are known for the constraint as well, but they're not great rates. They are not rates that make you happy. They're exponential in the dimension or something like that. So yeah, so that's the open problem in the convex concave domain. And if you're into optimization, that's a very concrete open problem to work on. In the non-convex, non-concave setting, as I said, any method will be super polynomial.
Okay, yeah,
unless there is further structure in the problem. For example, Panagiotis here has some work on relaxing convex concave. I mentioned the citation in the beginning of the talk, but so Panagiotis, in a recent paper of mine with Yelena Diakonikolas and Mike Jordan, we have ways to relax a bit the convex concavity and still get asymptotic convergence. So part of the game, like like from the upper bound and the lower bound, right? So you're trying to chip away special cases of non-convex concave settings where you can still have convergence of learning algorithms. So there are certain cases known, and you want to do more work in that. A particularly nice special case of that I like is a two-player zero-sum stochastic games, like Shapley stochastic games. Over there, the objective function is not convex concave. Nevertheless, the min-max theorem holds. And I have done some recent work that will appear in NIPS, but generally it's a very interesting problem to think about optimization in this special case of the problem. So in general, work on positive results has to chip away non-convex, non-concave cases where you can get algorithms. For the general problem, all you can hope for is asymptotically converging results, and I have some work on that sort of like is very much like a path following type of methods. That result from the connection to this Brouwer fixed point theorem.
Thank you.
If I may, because I realize we have to the GameNet people will have to leave because there is a meeting right after, unfortunately. But I couldn't resist taking the opportunity to also thank you, Kostei, for the great talk. And if possible, I only have a quick low-level comment and a high-level philosophical question where I'd like to hear what you think. The low-level comment had to do with Abraham's question about extra gradient in the beginning and what you were saying also about the differences between extra gradient, optimistic gradient, and the gradient descent. And what is interesting is that they actually all are discretizations of the same gradient flow because they are all Robbins-Monroe algorithm. And the degree to which this discretization actually holds is controlled by the Lipschitz constant of the gradients, which is a second order smoothness condition, and which what is interesting with respect to what Abraham was saying is that even though these are first order methods, they are implicitly relying on some second order condition for them to work. But the high level question I had is the following. In general, if you take a general n-player game with continuous payoff functions, then solving that problem is as difficult as determining the invariant sets of any dynamical system. Now, would you think, and of course this can be very complicated, have much more complicated structures than cycles or what have you. Do you think that there is a gap between two-player, I mean, min-max optimization and more general n-player games, or have we already got all the difficulty the moment we get out of minimization and we go into min-max?
I mean, so what I showed is that, you know, the moment you make the objective function non-convex concave, you already get.
Yeah, for sure. I am interested only non-convex,
complexity.
non-concave. Yeah.
Right. So I guess so what the results show is that, yeah, the moment you make the function non-convex concave, you already got all of PPAD. So the only scenario wherein there is a difference is, you know, if you're thinking about problems that are not even in PPAD. But I don't know how this would look, but like sort of like, you know, like once we start considering, for example, mixed strategies over continuous sets, I can very much imagine situations where there is no succinct description of the object you're trying to compute anyways, so that you're not even in NP. So I can certainly think two-player or multiplayer cases that are not even in NP, but like sort of like if you're sort of playing the game that I've been talking about now, where you have a real vector, but you really are looking for pure local, pure equilibria, I think that we have, yeah, that you know, that we're close to capturing the full complexity there.
Okay.
Like, you know, like to say it differently, only if the problem only if the thing you're trying to compute is not guaranteed by fixed points theorems, by Brauer's fixed point theorem, you can potentially have something outside. So I don't know what that would be, but yeah, so it has to be non-provable by Brauer's to be to be not captured here.
Okay, thank you. Thanks a lot again.
Thank you all. And thanks again for coming. Thank you for the talk.
Thank you very much. Yeah, thanks for staying. Yeah, thank you.
Everybody.
Thank you very much, Kostas.
Bye, Bernard.
Bye, take care.
Bye, thank you.
Bye, everybody.
Bye, everybody.